and see if it looks good, and then I'll let you take it away.
Yeah, because there is an option called presentation here. So I can just upload my presentation, I guess.
You can try sharing. It might be easier to try to share screen. Yeah.
Okay, let's go. Yeah, can you see my screen?
Yeah. Best of luck, by the way. Yeah.
Yeah, I'm ready, Nathan. We can start.
Okay. Yeah. Get started whenever. Yeah.
Yeah. Good evening. This is Rashmi, and today I will be presenting Enterprise Synth, Agentic SFT plus eval data from API schema without live execution. So I have used zero API keys with zero calls and deterministic schema checks. Thank you, Nathan and Spurti, for having me here. Enterprise Synthetic is a schema aware agentic framework that synthesizes high quality, supervised fine tuning and evaluation data sets. So, directly from open API schemas to completely offline with zero API calls and zero execution dependencies. I'll just walk you through a whole process how I determined this step of using open API with zero API keys, and I evaluated dataset from API schemas without any live execution. Okay, yeah. On the first note, I would like to explain what is bootstrap bottleneck. Here, the bootstrap bottleneck is a traditional agent training. Data comes from execution logs, where you run the agent against the live API repeatedly and record what happens. So, I would like to explain these four are the unviable limitations. The first one is the execution bottleneck, where you will majorly able to see what is traditional data generation, and also what kind of APIs it will start assuming, and what can be called as safely, and also what cannot. So here you can see the repeated of APIs during trajectory collections, which is highly brittle and also prone to live system state failures. So this is the execution during the bottleneck. And the second limitation is the sandbox. What exactly is sandbox? These are used in enterprises. Those are majorly APIs. Those are frequently unavailable or expensive, and also mostly like impossible to execute or isolate in local developer staging the environments, and also um, it will show a blocking of rapid testing. This is the major sandbox limits. And also in a big enterprises, the safety and also privacy risks always matters. Here, what I saw is live system execution always traces and also exposes the corporate credentials, which is highly valuable and also highly sensitive with the proprietary data and sensitive operational pipeline with this behavior for the external telemetry. So this is the major limitation which I could see when I was researching more on what's the bootstrap bottleneck for the enterprise synthetic. So when it comes to rate constants, here this limitation majorly shows us what's the strict quota ceiling and also infrastructure rate limits make the automated large scale trajectory collections extremely slow and also fragile. So this is the major prone which makes the sudden timeouts. So this is actually a major limitation for every enterprises there. So yeah, next is like what is the system overview. Going on, I would like to explain what kind of system overview I consider and why is this very simple and also doable. In this, I would like to explain the specifications that try to replace the live code to enable the schema aware in the offline synthesis. What exactly is offline synthesis? As we mentioned before, here we can see no live APIs can be used. So the whole process is done offline. First is input. In input, we can see Open API specification. Here, what exactly Open API specification meant is the structural API that has a description files and also contains the endpoints, which has more query in structures and also schemas and object parameters. All these are very important for an big enterprises. And also the next step, considering the input is the structural API, the next step starts with the process. In this process, we will see schema aware synthesis. Around this aware synthesis, we could always see the automated pipelines that will start parsing the descriptions from the files to generate the intent trajectories and also validate the structured outputs that's offline. So here comes the main process. The whole process is done offline and the output is also given offline. So this is the major changing step where you can consider. So when it comes to output, these outputs are always verified traces where companies can consider doing it, which is completely multi-turn tool use traces. Those are ready for supervised agentic fine tuning and also benchmark evaluation. Most of the companies feel like if the multi-turn and the multi-tool use traces are ready for the supervised genetic fine tuning, then this is the best process to consider for every company out there. So the central thesis of this whole system overview is considering the agent behavior that can be synthesized directly from the interface structure rather than code execution. So synthesized datasets provide strict offline verification with zero API calls and zero execution dependencies, which is always a privacy and also the security that's always safely managed here. Next comes the synthesis pipeline. This is the four major stages pipeline which I worked on. In order to explain this, I would like to explain what exactly this four major pipeline compresses of. This is majorly a verified SFT datasets that I have used. I have used API gurus. Among those, I have took 45 examples of dataset and I started dividing them into the four stages. Every example has a different stages, but I have considered major examples that has these all stages that will process. So the first stage comes here is API schema parsing. Under API schema parsing, you can see extracting the functional endpoints, methods, and validating the patterns where it gets the request and it will start responding. And also, it considers the models and also authentication, those are required directly from the raw schema structure, and it will start parsing to the expected output. This is the first stage where it will start parsing the functional endpoints and also methods. Next stage comes intent synthesis. In this stage, it will start from the process where it needs to generate a rich and highly realistic agent task instructions and system objectives, where it is highly tailored specifically for each discovered API endpoint in order to match their capabilities. Under intent synthesis, it majorly performs instructions that's been given for the agent. So under intent synthesis, the whole agent task instructions are done. So the next step comes here is trajectory generation, where we will see the multi-turn and also tool use that's been given for the agent to trace the consisting of natural reasoning steps and also target tool selections, which has a exact parameter maps and also matches the expected responses, which doesn't miss any parameters and also doesn't make any mistake. So this is the major stage, the stage 3, where you will have the expected output and also you will have a reasoning steps to follow. So after this, immediately we can go to schema verification, which was our targeted stage 4 and the final stage, where here you can see when the subject is very constructed towards the trace, and also it also follows the strict schema validation. This filters out the parameter errors and also missing fields or any incorrect endpoints to guarantee you the expected output and also the quality of the output. This is the whole four stage pipeline that has been compressed into a four stages. So here comes verification by construction. That does mean it's just determining the schema aware and also what is the verification benefits that exactly enterprises follow. So deterministic schema aware checks follows four types. First one is endpoint and method existent. This majorly validates the targeted endpoint and also associates the existing schema for the enterprise. So required fields, those are present, will always guarantee all compulsory input keys, those are populated in the parameters. That will make sure it will not miss any important keys. And also the third one which will follow is strict type and format matching. Here it ensures all kind of object types that matches the validation types. And also trajectory step completeness is a major step where it starts verifying the trace and represents a closed with the logical multi-turn operational goal. These are the four steps where every enterprise should know in the deterministic schema where. Under verification benefits, what exactly enterprise should follow? Here are the three steps. Automated data quality gate, which follows the traces with the parameter synthetic faults and also incorrect endpoint schemas or wrong structures, those are completely rejected prior to storage. So all the enterprises need a no live API execution required, validates full complex API client interactions. This is the major focused area. And also enterprises always focus on safe and repeatable and auditable APIs where they can use and they can proceed. So the evaluation design is made on three topics. That's held out domain, test model, and compact data set. Under this held out domain, I have considered Zoom API to be a domain. Under Zoom API, I have used a testing model as Quint 2.5. So the model Quinn is evaluated on the Zoom API, which was completely held out during schema SFT synthesis to verify true out of domain transfer and generalization. So, after this held out domain, we can go to the test model. Why I considered Quinn 2.5 is because this is very highly lightweight and can find we can use until to fine tune the zero point 0.5 billion data base model, which is fine tuned to explicitly prove whether strict schema constraints and logical agent structures can be easily learned. So actually Quint 2.5 is very good model, I would like to say, which has trained my 45 examples in just 3 to 5 epochs and gave me the low loss rate. So yeah, next comes the compact data set. Here I have considered 45 traces, that does mean 45 examples, to stress test sample efficiency and also training uses an extremely small focus set of just 45 traces example run over three local optimization epochs. So next we will see the evaluation result. Here in evaluation result, you can see there is an held out API, that's Zoom, and that's been tested base versus fine tune. For the fine tuning, we have used Quen 2.5 model. After using Quen 2.5 model, the tool selection under enterprise synthetic will be 87.5%, and also the parameter validity will be 57.1. There is a huge difference between the base and the enterprise synthetic fine tuned model after using Quen. So here you can see LoRa fine tuning loss. I have used LoRa fine tuning too because the LoRa and the Coin matches so well, and it will give you the training loss very less. Even just in third epochs, I could see 0.24 training loss, which is very good. So after seeing the training loss, I could say that three findings that proves the SFT viability and successful tool use transfer. Those are viability of offline synthesis and robust data quality filter and efficient generalization. These three are majorly important for each and every enterprise out there if they want to work on all the APIs in offline. So the future work says the proof of concept, those are boundaries, reveal the three pathways for multi API scaling. Under the present research boundaries, I could find the compact training set that has a limited to highly specialized 45 example set as a late weight verification and single held out target that has a current transfer verification for focused exclusively on the Zoom API. So the sub 1B base model would be Quen 2.5, and static trajectory sets currently does not implement ongoing operational feedback from active views. So this was the present research boundaries that I could find, and the future scaling research would be mainly based on the hundreds of API to the scaling part, and also testing larger models like llama 3 to 8 billions, and also queen 2.5 to 7 billion data. And also considering the active feedback loops from human and AI feedbacks would really be very good part to work on in the future on this topic. Thank you. Any questions, Nathan?
Hey, Rashmi. Thanks so much for an incredible presentation. I really enjoyed it.
Yeah.
You should be really proud of the amazing work you did this summer. I think you did
Yes.
a fabulous job.
Yeah,
I
Nathan.
do have questions. I'll ping you on them like after the talk were like over time. But
Yeah.
really, thanks so much for a great job, and I'll see
Yeah.
you soon.
Of course,
Hopefully at the
Nathan.
summer party. Yeah.
Yeah, thank you, Nathan. Of course, I'm just waiting to meet you in the party.
All right. Well, see you soon. Great job,
Bye.
Rashmi.
Yeah.
Bye.
Bye bye.
Hey, Gideon. How are you?
Hi, I'm good.
Awesome. You want to see if you can share your screen and
Yeah, let me share my screen. Um, okay. And let me check.
yeah, you think you should be good, right?
Okay, yeah. So yeah, hello everyone. I'm Ian Chen, and this is a presentation summarizes my work as a software engineering intern at Anote. The main theme connect to my internship was reliability. I began by studying why multi-agent orchestrate falls silently, and then applied it the same uh, and applied it the sorry and applied the same reliability mindset to Panacea runtime testing, integration, and the release processing. I will recover three parts: my product engineering contribution and the Oxbridge bench research project, and one GTM lesson about evaluating technical work against external standards. So my work connects three layers. First, the research layer focuses on understanding orchestration decision, whether a router choose the right path, whether a system recovery, and how far a error separated through the system. Second, the product layer focuses on making Panacea safer to run and safer to release. And this became my main execution track in July. And third, the GTM layer test whether technical work was packaged clear enough, and whether it met external reviewer standard. In total, I had 14 Panacea PR merged, one producible benchmark and paper, and three assigned GTM opportunities. And uh, this slide is an overall map of my product work. It was not one isolated feature. And the first stage was a runtime safety, startup behavior, uploads, streaming, model configuration, and key health. The second stage was um, learning infrastructure, including model drive routing and opt-in feedback signal. And the third stage was security and testing. And dependency cleanup, removal of unused code, log and access control fix, and higher backend coverage. The final stage was integration and release verification, including the web integration and deployed build identity and capability and parity between the CLI and the VS Code extension. The common thread was controlled failure, prevent predictable failure, and make unexpected failures observ- observable, and verify recovery before calling something completed. So here's a for example. Uh, for uploaded, the PR reject this PR reject overrides the fields before reading the full body into application memory, and isolated fields, so one bad file doesn't necessarily for an entry bench. For this, um, the PR updated the client with the backend actually token actually token construct across web, desktop, and mobile. For streaming, this PR added the correct servo send event headers, so proxy don't buffer agent responses. Finally, and these two PR like improve the configuration behavior. The application can start locally without every external secret, and expose a privacy safe key health signal without revealing the secret itself. So these small changes individually, but they protect the request pass user hint first. And uh, this was the very clear connection between the research and my product. Ostrich bench shows that routing based only on keyword or service flag can fail when the wording is misleading. Instead of replacing Pacini routing outright, the PR 222 introduced an opt-in um, model driving routing path behind a failure flag. It asks a structured intent decision, but if the model calls false, sorry, the system safety fallbacks to exiting keyword result. The so it made the experiment reversible and default off. So this PR um, and the PR 248 then added up the feedback storage and signal for rapid follow up behavior across servo, chat, and questioning answering paths. And the important boundary is that I created measurement infrastructure. So the next group of contribution reduce release risk before deployment. So this PR 264 rise the backend task coverage from about the 81% to 92%, with 114 test passing across a workspace database behavior authentication and document coverage is not proof of correctness, but it gave the CI gate more margin to detect uh, regressions. So the PR 232 upgraded active desktop and mobile dependency, resolving serious mobile issue and reaching zero reported desktop vulnerability, while nothing that physical device smoke tasks still need to be completed. And the PR233 remove a top level front end, and it's that see I job after um, the scope, and that removed the two serious uh, alert from unused code. and um, and this PR was major integration task. Susanna built the original feature set in PR 249, including web document chat, usage billing, and infrastructure changes. So my contribution was to integrate that work into the current main branch, resolve a conflict while preserving the existing marketing and the uh, regression and flow, and harden the billing boundary. In particular, strip plan and prices was select a servo slide instead of trusting client supplied values, and webhook claims are released after business processing failures, so an event could be retried safety. So I also re uh, require the redocument build production build pass and invalidate the combined branch. The final checks included the 228 backend task and the 86% backend and coverage, and no production npm edit findings. And one operation list was that the deployment workflow finishing successful doesn't prove which code was actually live. The PR 267 merged into developed added build identity by injected that the git sha and exposing no secret front end and back end metadata. It also adds read only smoke check for health, routes, anti authentication, and the billings without banded retries. The same verification can run manually or after deployment. So this matters because an API route can return a front end fallback page and still look successful. The scope is also important. It added verification check. It uh, didn't prove that every production dependency was health, and we still need to verify the deploying version, API, and security, and the database setup. And this PR combined the still uh, re- relevant agent work on top of the current undeveloped branch. It brings the same core capability to the COI and VS Code extension, MCP server configuration, and the runtime uh, wiring, plan model, web search, and web fetch, and permission flow for automatically discovery too. And now I will move from the product work to the research. Existing agent benchmark often tell us whether a pipeline success, but not why it failed. So Oxtrade bench treats three um, mechanism as a first class measurement. Routing robustness ask whether the orchestrator choose the correct task tool or execution model when surface queue are misleading. So this shows which failure recover and which keep spreading. So error separate measure how many late stage are affected by one inject error. The benchmark use controlled seed reproducible figure injection, exact grading, bootstrap confidence intervals, and the paired task were applicable. So this is a controlled mechanism probe, not a production domain leaderboard. And the first finding uh, concern routing. So on the 26 case task, the keyword and the flag measure was perfect when the clues were correct. When the clues were misleading or missing, its accuracy accurate accuracy dropped to zero. The model-driven routes ranked 100% on those reverse role case. However, the important result is not simple that the LLM is better. The description where TF-IDF routes also ranked 100% on the adversarial set. The mechanism lesson is that leading and the task description removed uh, the blind spot, and model complexity alone doesn't explain the improvement. It results motivated the rev- uh, reversible routing experiment I described earlier in Panacea. So the next experiment revived the three recovered ties tool figure recovery every time, unclear delegation recover only 30% of the time, three hidden figures, bad contact, conflicting result, and acting too early did not recover at all. So blind retry did not repair those small. It reproduced the same fault and increased the time before detection. We also find the dip effect as a pipeline dip increased from 3 to 7 stage. And the main and latent cascade radius increases from the 0.93 to 4.67, while the two fault reminded content at zero. And the order survived both long proof reforming and a multi-model sweep. Although the absolute rate changed together, this result suggests the retry is not a substitute for detection, attribution, and access to trusted state. And um, so my um, main learn is that reliability is a system property, not the final pass or full score. At the decision layer, a final score can hide the routing choice, the started, cascaded. At the recovery layer, retry cannot replace attribute and the trust states repair. At the delivery layer, test build identity and production rules must agree on what exact actually shipped it. And in reporting, merged, open, submitted, close, and production verified it are different claims. And the GTM works also like it's the same idea across the this three government and external benchmark opportunities. I um, researched the requirements translated to the Anote's technical capability into proposal, and use the external feedback to evaluate it. And I really learned a lot from this. Thank you. That's all.
Yeah, awesome. Thanks so much, Gideon.
Yeah.
You should be really proud of the work you've done this summer. It was really amazing, and it was awesome to see how much you grew and all the different PRs you worked on, and then like the orchestrate bench. And yeah,
Yeah.
I have a lot of
Thank you.
questions, but I know we're a bit over time, so I'll like ping you sometime soon. And
Sorry.
yeah, no, great job, and really appreciate your hard work, and thank you so much.
Thank you.
Yeah. Awesome. Well, that was a great presentation by Gideon. Yes, Lauren, are you here?
Yes, hello. Should I just present or?
Yeah, share your screen and take your time. Like, take as much time as you need. It's fine. Yeah. So.
Sorry about that. I'm just trying to get my tab to display. Okay, can you see my screen?
I can. If for some reason it's not all the way full, can you try to make it wider, I guess? Oh, that's perfect. Okay.
Okay. Okay. So, hi everyone. I'm Lauren, and my talk is on how failures propagate in agentic RAG systems. And just to define some things up front, RAG would be retrieval augmented generation, which would just mean a language model that looks things up in a document store before using an LLM to create an answer. And it relies on the context from the document that it retrieved rather than just relying on kind of its built-in weights and parameters. And then agentic RAG goes further. So instead of one retrieve then answer step, the model runs a loop where it issues a search, reads what comes back, decides if that's enough context, and then if not, continues this process until finally answering. And each of those rounds, one search and reason step, I'll call a hop. And so just to summarize what the work is that this paper is presenting, we're taking these multi-hop systems and then deliberately breaking one hop and seeing whether or not we can identify where the hop broke or at what step did the agentic system break, and then seeing if that that error propagated into the final output. So why is this hard? Like I said, an agentic RAG system interleaves three things across multiple hops or search and response steps. So it retrieves evidence, reasons about it, and eventually generates some sort of answer. And at each hop, the agent picks a subquery, looks up if it's retrieved, and decides whether to search again or answer. And this sort of flexibility and this non-deterministic behavior at every hop makes it hard to assign blame. So if you look at the chain here on the right, we have at hop 1, the evidence retrieved is irrelevant.
Lauren, I'm sorry. I think it's stuck on the first slide. I don't know. Okay, yeah.
Okay, yes. So that's what this. So yes. So looking at the 3-hop trajectory on the right, if the first hop retrieves irrelevant evidence, this causes some sort of downstream effects. And so we can't really identify the actual step in which that evidence is corrupted, and we just get a final ungrounded answer without being able to trace back to where the blame lies. And so this leaves two questions that my paper sought to answer, which were if a diagnoser can recover a known intervention hop after the failure has propagated, and what to do when sort of repair probes add information that the final trace is mixing. So if we're able to kind of put back in correct, relevant, grounded context after the agentic loop has finished. And so the 3-hop example on the right, again, shows an evaluator flagging a late hop, the ungrounded final answer, while missing the real fault, which is at hop number 1. Okay. And so here's the benchmark that my paper sought to produce in 3 steps. So first we'd inject, so we'd corrupt the trace prefix with the certified fault at hop H, so hop 1, 2, or 3. Then re-execute, so the same agent will run the remaining trajectory, and either it can propagate the fault or sometimes it'll self-correct, so this error will kind of get smoothed out by the final hop. And then score, so we'll evaluate each diagnoser against the known intervention label. And the crucial design choice here is that the downstream sort of response or suffix is a genuine agent reaction to the corrupted context. And it's not just something like tracing it stat throughout the whole benchmark. So this will allow us to study propagation and recovery on a variety of different error cases. And so here are the sort of different error cases that I added. So we supported 7 certified interventions, and I've grouped them sort of by what they attack on the screen. So the structural ones, empty retrieval, irrelevant documents, and query drift tend to be visible in the trace. And then misleading ones like false premises and stale evidence keep the evidence there but plant a sort of wrong claim, which will surface in the final answer. And then content corruption is a hidden case, and I'll delve into it a little bit deeper in the next couple slides. And early termination changes the agent's decision to stop. So in every one of these, the downstream suffix is regenerated in reaction to the type of fault that we've injected. And just to talk a little bit more on content corruption, it's the hardest case for agentic RAG systems to kind of self-correct and also to identify. So instead of changing an entire document, emulating when a document is irrelevant and retrieved, we just change one fact. So this would be if a document has corrupted or outdated information. And the documents still topically look relevant and structurally look correct. So the evidence still would look right to a typical diagnoser. And we pick which scan to corrupt by priority. So if a gold answer appears in the evidence, we corrupt that answer fact. Otherwise, we'd go for maybe an entity, like a person's name or a company's name, something that the agent would carry forward into a later subquery. And if there's no entities or answers, we'll fall back to just a generic entity or number, just ensuring that the information in the document is corrupted in some sort of way. And because we store the original and corrupted spans, so we have the original document and then the corrupted document, we can label the outcome deterministically without any need for like an LLM judge. And so we can determine whether or not the corrupted piece of content ends up surfacing in the final RAG system output. And absorbed means that the answer contains the changed value, which is kind of the worst case scenario. So the RAG system is just outputting kind of incorrect information. Resisted means that the answer is still correct, so the agent actually self-corrected throughout its agentic multi-hop loop. And derailed would be any other error case, such as hallucinations or ungroundedness in the final answer. And then we had kind of 5 diagnosers that we were evaluating in this paper. So 3 of them would be post hoc, which would be rule-based. And so this would be after the entire agentic system has finished. We're looking at the final output and trying to determine where the error surfaced or the initial failure happened and which hop that was present in. And so Dr. Rag used coverage gating to pick the earliest hop with insufficient answer support, and an LLM judge will read the trace. And then two of the other types of diagnosers are more active probes. So propagation aware would do frozen hop repair. So it would fix one hop while holding the others fixed. And so this would be the case where, say, a RAG system searched for some follow-up information based on the first three hops, then that follow-up hop had some sort of flawed retrieval. This propagation aware repair would fix only that hop and see whether or not this would lead to a correct output. And then suffix regen repairs a hop and then regenerates the rest of its trajectory. So if failure was kind of identified at hop number 3, then it would fix hop number 3 and then also regenerate hop number 4, 5, and so on and so forth. And so these two probes differ only in how they would treat downstream evidence. So whether or not we're keeping all of the other past hops consistent, or if we're actually regenerating and rerunning those follow-up hops. And this difference actually turned out to matter a lot. So in our measurements, we measured 4 things: attribution identifiability, which is exact hop accuracy over traces that stayed failed after re-execution, bootstrapping around 95% of intervals. And so this would be when we're checking the accuracy over traces that were re-executed but still produced failed outcomes. Counterfactual recovery is the fraction of interventions that still produce a correct answer, which is kind of a separate robustness outcome. Deterministic outcomes are the absorbed, resistant, and derailed labels from that original span pair. And then this is consistent across all of the passes, and it's judge-free, so it's deterministic. And then cost per correct diagnosis separates kind of the localization quality from being able to actually deploy it in a product. So seeing whether or not this will produce high quality outputs, and also if it's something that's cost effective and can be deployed in real products. Okay. And so this is the sort of headline structural results on a couple different models. So on Claude Haiku and 3-hop MusiQ. Coverage-based attribution is 0.91 at hop 1, but drops down to 0 at hops 2 and 3. So coverage catches the visible hop 1 fault, but once the agent is regenerating these follow-up hops, the injection signature is erased, and we're not able to actually trace back to that original hop and see also the type of failure that was injected at that hop. Notice that the judge in the frozen hop probe keeps some partial overlapping interval signal. So this is about lost post-hop information, not just end-to-end task accuracy. Okay. And then on content faults, the picture changes in an interesting way. So at hop 2, coverage gets 0, but the frozen hop repair reaches 0.67. And so this gap comes down to scope, actually. So suffix regen, that one kind of probing diagnoser and fixer, regenerates the trajectory. And when it does, it retrieves clean evidence and accidentally removes the very fault we're testing. So it drops that down to around 11%. Frozen hop instead kind of preserves the corruption everywhere else. So anything that was generated as a follow-up to sort of corrupted context stays corrupted. And so because of that, we can see very clearly that each hop in an agentic RAG system is very tightly interleaved, and you can't really treat a single hop as a vacuum, as the context and the subsequent hops are tightly coupled. So the context and results from one hop will impact all of the downstream hops in an agentic RAG system. Okay. And then these sort of deterministic outcomes, so classifying something as absorbed, resisted, or derailed, show what actually happens to the final answer, and also shows whether or not agentic RAG systems are able to recover. So absorption is answer shaped. So 20 of 22 absorbed cases are answer fact corruptions, and 0 of the 40 entity corruptions are absorbed. That is whenever a clear question answer is corrupted, that ends up getting surfaced in the final answer. And entity corruptions are less likely to be surfaced in the final answers. And then query contamination is only 3 of 129 cases, which means monitoring query text alone, so the query that yields a retrieved document, would miss almost all of failure propagation. And so the takeaway from this slide is just that the corrupted value resembling a direct answer is often repeated, while a corrupted chain length more often just prevents a coherent answer. And so for final takeaways on this paper and on my presentations, there's 4 things that are really key. 1, propagation erases post hoc signal. So once the suffix or the subsequent hops are regenerated, no amount of tuning like coverage threshold will bring back the information that was overwritten. 2, the 2 probes ask genuinely different questions, and each one credits a different position in the causal chain. 3, recovery is its own separate outcome. So a correct answer after we injected a fault tells you that the agent was resilient, not that a diagnoser was able to actually fix any error at any specific hop. So the agent was able to self-correct rather than a diagnoser effectively repairing one failed hop. And 4, propagation depth deserves to be its own explicit axis when we evaluate these systems, as the recoverability dropped drastically as the number of hops or propagation depth increased. So a failure at hop 2 was pretty recoverable at hop 3, but it was almost impossible to recover at hop 5. And this is something that people who are aiming to create diagnosers or find ways to improve robustness and correctness of agentic RAG systems should be aware of when evaluating failure cases in their systems. And then just briefly touching on limitations and possible follow-ups, there's not like to be upfront about the limits. This isn't a complete sweep over every single backbone dataset in depth. So strict, dense, hot pot QA gave us too few failures to compare because the agent recovered almost everything. And then there are a couple failed cases at depth 2 and depth 3. So it's hard to create exact causal claims based on the number of failed cases present. Also, our corpus stays clean, so it means that re-retrieval can heal some sort of faults. And so if something was failed and then the agentic system goes back to our corpus to get some sort of follow-up information, since it's pulling from a cleaned corpus, it might be self-correcting at a higher rate than a production RAG system would. Now for feature work, we'd maybe want persistent corpus corruption, so a failure that was injected into a RAG system or agentic RAG system is also reflected in the document corpus, so that it continually pulls sort of failed documents and seeing how the agentic RAG system responds to that. And then also more path-aware diagnoses or diagnosis frameworks that would pick a probe based on the suspected fault type based on the answer outcome. So identifying how would be the best way to see where the failure occurred and which hop it occurred based on the final structure of the RAG output. And then also expanding the sample size so we can make real inferential comparisons. So just to wrap up, 3 numbers capture the biggest takeaways from my paper and from this presentation. So coverage attribution goes from 91% at hop 1 to down to 0% at later hops. So propagation erases a post-hop signal. Essentially, as I said, you're able to pretty easily recover or identify failures when you're going from hop 1 to hop 2, but when you're going from hop 1 to hop 4, it's almost impossible to identify that the error or the failure occurred at hop 1. Frozen hop repair recovers hidden content faults at kind of depth 2. And so it reaches about 2/3 where coverage gets nothing. So kind of fixing one specific hop and then continuing the agentic RAG system performs a little bit better than just trying to retrace your steps and identify where that failure occurred. And 15% of hop 1 corruptions get absorbed into the answer word for word. So a failure on the first retrieval and response step will actually still surface in the final answer 15% of the time. And so remembering one thing, propagation depth is very explicitly coupled with how failures propagate in agentic RAG systems, and we should be very mindful of how failure cases might arrive at each individual hop and adjust the recovery and diagnosis frameworks that we use for agentic RAG systems accordingly. Thank you so much. I think that's about it for my paper, and I'm happy to take any questions now or later.
Awesome. Well, thanks so much, Lauren. This is a really insightful presentation and incredible research. And I do have a lot of questions. I'll definitely ping you on them on the side. And just wanted to say, like, I really appreciate all your hard work this summer. You've done an incredible job, and just very grateful for you being part of this. Yeah.
Okay, thank you. Bye.
Hi.
Hey, Hannah. How are you?
Sorry. Hi.
Yeah. Hi. How? Yeah. I guess I said
Good.
that already. But yeah. So feel free to take. I know it looks like we're over time. Just take as much time as you need. No rush. I'll for the next call, I'll tell them to like go at a different time. So you have like 18 minutes. So yeah, don't worry about. It. Just take as much time as you need. And yeah, best of luck. Yeah. You want to just make sure you can share your screen and then you can kind of get started. Yeah.
Okay, let me just check. Cool.
Cool.
Oh, oops. You got the I think it's fine. Okay, cool. So I'll just get started. So hi guys, I'm Hannah. And together with my teammate Zeray, we will be presenting the paper Retrieval Bench, Chunking and Embedding Choice as First-Class Variables in Cross-Domain Retrieval Evaluation. So let me start with the motivation. When people build a retrieval system, they face two early, seemingly independent choices: how to chunk their documents and which embedding model to use. Conventional wisdom treats these as a minor engineering choices. So this paper's central claim is that chunking strategy and embedding choice are first-class variables with effects that are large, interacting, and domain-dependent, deserving the same rigorous study as a model architecture or training data. Existing benchmarks like BIR evaluates on a fixed corpus or atomic passages, freezing the chunking decision. So the benchmark takes the same source document and indexes them under different segmentation policies, then retrieves with different embedding model. The design cross 4 independent axes, 12 domains, 4 chunking strategies, 3 dense embedding models, and BM25 as a sparse baseline. And each of the 12 domains reuse existing IR datasets, so the queries and relevant judgment already exist. Familiar BEIR style sets like TREC COVID, PhiQA, Argue ANA, NF Corpus, SciFact, SciDocs, Natural Questions, Fever, HAPA-QA, DBpedia Entity, Quora, and Open Domain QA sets. So there's an important caveat that need to be stated specifically. Because of the subsampling, scores support comparisons among configurations on the same sample corpus. They're not directly comparable to numbers of full corpus leaderboards like BIR. So this is a deliberately internal comparative benchmark. The 4 chunking strategies are the heart of the setup. fix 512 cuts into 512 words windows with a 50 words overlap. Sentence use NLTK to group sentence into a non-overlapping windows of a 3. Recursive splits on paragraphs first, falling back to sentences. Semantic greedily merges sentences, while cosine similarity stays with above 0.75 using OpenAI embedding for boundary detection. So this fourth strategy spans spectrum from purely structural, fixed 512 to purely semantic chunking with sentence and recursive seeding in between. Note the semantic chunker uses the OpenAI embedding model for boundary detection, and we flag this as a potential confound since the same model is later used as a downstream embedder. Sorry. So the primary metric is NDCG at 10. The system received top 50 chunks, but relevance judgment are at the document level. Then we max pull chunk scores up to their parent documents, then evaluate the top 10 unique documents. All dense embeddings are L2 normalized scores by inner product. BGE and E5 use a model-specific query and passage prefix. And to quantify whether the chunking or embedding matters more, we introduce two indices via variance decomposition. CSI is how much score varies when you change only the chunker, holding the embedder fixed average over all embedders. And ESI is a mirror stage. So if CSI is bigger than the ESI, changing the chunking strategy moves quality more than changing embedding model, and vice versa. We also use the bootstrap confidence intervals to pair test that is full setup. And next, I'll hand it over to Ziri to walk you through the experiment and results. Wait, is it too fast?
Oh no, it's good. Yeah, you're good. Yeah, great job, Hannah. Really appreciate it, and thanks for doing an awesome job this summer. Yeah, you did it. You did great. Yeah.
Thank you. Considers the pre-experiment and evaluation metrics, and the full experiment will be run through by Ziray. Talk you guys through. Yeah.
Okay. Yeah. Well, thank you. You did amazing this summer. You should be really proud of your hard work, and yeah, congrats. Yeah.
Thank you too, though.
Yeah.
Okay.
Hey, Elaine, how are you?
Sorry, I was muted. Good, how are you?
I'm doing well. Yeah. You want to just make sure you can like share your screen and stuff, and then feel free to get started. Yeah. Just make it full screen, maybe.
Is it full screen to you now?
It wasn't full screen. I try one more time. Yeah.
Okay. One second.
Okay, awesome. You should be good to go. Best of luck. Yeah.
Sorry, wait, do I do a introduction?
Yeah, you can get started whenever. Yeah.
Okay, sounds good. Hi everyone, I'm Elaine. My research this summer was about why AI systems still struggle to answer questions from financial filings, even when the answer is technically present in the documents. This project started with a common assumption in RAG development. If retrieval is weak, we can improve it by using better chunking, re-ranking, metadata, query expansion, or a hybrid system. My main result is that this assumption mostly failed on SEC filings. I tested 7 retrieval configurations on Financial Bench, and the strongest conclusion was that not one clever retrieval technique won. The stronger conclusion was that the underlying document representation was broken, especially for financial documents and tables. It is easy to say that the GPT is bad at reading financial documents, but several stages happen before the model ever sees the evidence. A filing is parsed, split into chunks, embedded, searched, and only passed to the language model at the end. My project found that the biggest failure often happens early in this process. Financial tables contain headers, row labels, years, units, and signs, and need to stay connected. And when chunking process separates these pieces, retrieval searches over the incomplete fragments. At that point, a re-ranker can only reorder broken fragments. Query expansions can only search from those broken fragments more creatively. A stronger language model or a better retrieval strategy cannot reliably answer questions from evidence that was never perceived correctly. So for this experiment, I compared 7 conditions. They are first of all, it's the baseline testing, and then there's semantic chunking, recursive chunking, cross-encoder re-ranking, metadata enrichment, high query expansion, and a full hybrid configuration that combined multiple of these methods. This design matters because if I only compared the baseline with the individual or with the full hybrid, I would not know which component helped and which component hurt. So conditions C1 through C5 isolate individual retrieval choices. C6 asks for a more realistic engineering question. If I combine several or multiple retrieval stacks, does the system finally become a lot better or is more efficient in this process? And the answer was surprisingly close to no. For the design of this research, the benchmark was a finance bench, which contains questions over real SEC filings. The original evaluation had 150 questions. I only used 133 because a source of the 17 questions could not be retrieved for this research. The questions fall into 3 categories. Metric-generated questions are often numerical. Novel-generated questions test more varied reasoning, and domain-relevant questions resemble the kind of qualitative questions that an analyst might ask. I evaluated each condition under 3 main sources: RUGL, exact match, and latency. RUGL is the standard overlap metric used in Finance Bench. Exact match checks whether the correct answer appears anywhere in the output, which is very useful for short numerical answers. Latency captures the operational cost of adding more stages to the pipeline. So the core result of my research is that there is no meaningful improvement using a different retrieval strategy, because across all 7 conditions, the entire RUGL range was only around 0.017. The baseline achieved a 0.177, and the hybrid, despite combining multiple retrieval strategies, achieved a 0.78. It is an improvement by only 0.001. So none of these enhanced conditions produced a significant improvement over the baseline. This matters because the hybrid is the exact system many teams would build when trying to strengthen the RAG system. It includes larger chunks, metadata, plus dense retrieval, re-ranking, and query expansion. But in this experiment, adding those components mainly increased complexity and latency rather than accuracy. The result is negative, but it is very useful. It is telling us that retrieval optimization sometimes is not the main bottleneck, and this prevents us from investigating further in the wrong direction. This slide combines accuracy with latency, which makes it clearer for us to see where the trade-offs are. Recursive chunking, which is the second method, is the only enhanced condition that is matching with the baseline's RUGL while keeping latency almost identical. Semantic chunking and re-ranking are both around 3 times slower than the baseline. The hybrid takes approximately 50 seconds, which is around 4 times slower. Even though the hybrid technically has the highest Rugel score, it is not very efficient. The improvement is negligible, and the exact match score is actually worse. Semantic chunking is an important exception. It is slower and performs worse under overall Rugel, but it produces a very strong result for exact match. This is just that semantic chunking is not necessarily better, but it might be useful as a specialized route for numerical questions instead of just regular questions. Here are some of my main findings from this research. Finding one is that the hybrid is inexpensive ornamentation. So this pipeline looks sophisticated, but it does not address the real failure in the retrieval process. The hybrid combines recursive trunking, metadata enrichment, dense retrieval, cross-encoder re-ranking, and high query expansion. It achieved the highest Rugel score, but it is only an improvement by 0.01. It also has the lowest overall exact match score and the slowest latency. So the pipeline performs much more work without delivering a very meaningful accuracy improvement. The broader engineering lesson is that we should not be stacking strategies and just different ways of retrieval automatically. We should evaluate each stage more carefully before adding everything up together. The second finding from this research was Rugel highest numerical accuracy. So in the first place, we were only looking at Rugel to find the accuracy between the result and the base documents, but semantic chunking has one of the lowest overall Rugel scores, but achieves the highest exact match on matrix-generated numerical questions, which means that selecting a retrieval strategy using Rugel alone would produce the wrong recommendations for different types of question answering, especially for numerical financial question answering. For example, a model may correctly calculate the number 24 for this question, but the explanation is different and the wording is different. So then the Rugel score would be a lot lower than we expect. But also just looking at exact match is also imperfect. It does not confirm that a member exists in the right context, unit, or assign, but it reveals an important signal that we should be looking at Rugel and exact match and also other things to measure the accuracy of our results. The third finding was that metadata enrichment is very unstable. After running a few C's of the fourth experiment, which concerns metadata enrichment, I found that it is very unstable throughout the stages. First run had a score of 0.161 and it dropped to 0.146 in the third run. It is likely because that the tokens can dilute or destruct the semantic embedding signal, depending on like the stochastic behavior of the retrieval and the generation pipeline. But it just shows that a single run RAG evaluation can be misleading. A component might look very unhelpful, mildly unhelpful under one run and actively damaging under another one. So why did this system fail? Financial documents and financial tables are not simply collections of text. A numerical value only makes sense when it remains connected to its row label, year column, or unit. PDF text extraction and token-based chunking frequently separates those elements. For example, a query asking a capital expenditure in fiscal year 2022 may retrieve chunk containing capital expenditure, but not necessarily retrieving connecting the 2022 to that value. Alternatively, it may retrieve a sequence of values without like table headers, labels that identifies what it's connecting to. So I think when that happens, the answer is no longer available, and the model is not viewing this evidence as concurrently as possible. So re-ranking cannot reconstruct the original table. I cannot reliably infer the missing row column relationship. So the approximate fix is table-aware parsing that preserves financial documents as structured objects for future research. Yeah, so there's no evidence or explanation to see where exactly the pipeline failed, but a question can fall on PDF parsing, chunk creation, re-ranking, answer generation, or evaluation. If the table is already fragmented, then even a very capable retriever or re-ranker has little chance of recovering the answer. So a better evaluation system would save a detailed trace for every question. That trace can include the original extracted text, chunk ID, retrieval ranks, retrieval re-ranker score, the context passed to the model to generate an answer, and the metric results. By building a system and evaluation system like this, it would allow us to clarify failures by stage rather than testing the whole RAG pipeline as one black box. So from this research, there are some practical recommendations for using which strategy for retrieval, just based on like the numbers that I got. For general Rugal performance where low latency settings, baseline or recursive chunking is sufficient enough. Recursive chunking is a safe alternative because it matches the baseline's F1 and has ideally identical latency. For numerical questions, semantic chunking is a strong alternative. It has the strongest result under exact match, but I would investigate further to see if it is a great strategy or it is just an evidence that numerical questions should be separated from other questions to have a better result in retrieval. My research found that C4, which is metadata, and C5, which is query expansion, both has low accuracy and like unstable across stages, so shouldn't be used shouldn't be used too much. But the most important recommendation is to invest a upstream to investigate how we could parse the tables more efficiently before adding more retrieval techniques. So future work, the future steps of creating a better system would be first change the document representation, can change the financial tables to be more extractable, or changing the system so that we can preserve headers, row labels, values, units, years, and page references within a financial table. The second step would be question type routing. We should separate numerical types, numerical questions from qualitative questions, and then see if different strategies work better on different types of questions. And finally, I would introduce controlled stress tests. Examples include removing table headers, shuffling year columns, separating rows, changing units to see if where the retrieval has gone wrong. Yeah. To conclude, the main lesson here is that bigger RAG system is not automatically better. A automatically better RAG system. I've tested 7 common retrieval improvements on none significantly outperformed the baseline under Ruga. The full hybrid was visibly slower and did not improve exact match. Semantic chunking was one that was useful for numerical questions, but we should evaluate further using different tests and further testing. Metadata enrichment was very unstable across like the tests, and the next version of this research should make this the evidence object more explicit, preserve table route questions based on their types, save detailed traces, and stress test the pipeline against the exact document that it is expected to handle. Yeah, that's it. Thank you.
Yay. Amazing job, Elaine. Fabulous presentation and really awesome job this summer. Yeah, congrats on doing this. Yeah.
Thank you so much.
All right. Cheers. I'll probably follow up with some questions offline, but yeah.
Okay.
Thanks
Sounds
so
good.
much. You should be proud. Yeah.
Yeah. Thank you so much. Bye.
Hey, Alyssa, how are you?
Good. How are you, Natan?
Doing well. Doing really well, actually. Yeah. All right. Are you ready to give it a go?
Yeah. Let me just. Can you see my screen? Okay.
Yeah, I do. That looks great. Awesome.
Hi, everyone. My name's Alyssa, and today I want to focus on Anote's go-to-market initiatives through 3 different lenses: the problems our customers are actually facing, how Anote actually solves them, and how we're growing our community and presence to reach even more of those problems. Before getting into it, here's how I want to think about this. A proposal or a submission is just the moment we make first contact with a customer. That's our go-to-market motion. But the interesting part really is everything that happens after that. What's the problem underneath it? Does our technology actually fit? And do we have what we need to deliver? That last piece is where community really comes in, and I want to make sure that that's not an afterthought today. Let's first start with the technology since it shows up in everything else. At its core, Anote is a human-centered AI platform. We help teams label data, train models, and evaluate results so that they can build AI agents that are actually reliable. For customers who need that disconnected from the cloud, we can take that same platform and harden it so it can run self-hosted and fully air-gapped. We've proven that this works. Our Dash 3 demo hit 100% schema accuracy across 227 outputs with under 97 seconds of latency. So that's the foundation. Let me walk through how 4 real problems came up throughout the summer and how that foundation actually held up against each one. First problem, customers who simply can't use cloud AI. Picture a defense or intelligence team that wants to use AI, but their data can never touch an external server because of classification or policy. That's not a preference, it's a hard requirement, which means that most commercial AI tools are off the table before the conversation even starts. Our self-hosted air-gap setup solves that directly. But here's where community really matters. These opportunities need cleared personnel and teaming partners, and you can't find those relationships in the middle of a proposal window. They have to have already existed. That's exactly what our research fellowship and community events are building towards. A bench of relationships we can draw on before we're up against a deadline, not while we're scrambling. Second problem, deciding where to position resources without knowing what's coming. Military planners often have to commit assets and supplies before the situation is even clear. Get it wrong, and it's very expensive and slow to fix. This summer, with one of my colleagues, we worked on a research paper building a decision optimization framework for exactly that kind of uncertainty. And what I really want to point out here is that this research did not come out of nowhere. It happened because we stayed connected to the right academic and research circles. That's a community in research form. Growing our presence in that space through the paper itself and continued engagement with the Dash community is what turns a single paper into an ongoing pipeline of future work. Third problem, too much raw data and not enough usable insight. Sensing and surveillance teams collect far more signal than any other person can actually review, so the important information gets buried behind all the noise. Our work positioned Anote as the layer that turns raw data into something a person can actually use. Now, I want to be really honest here, because this is the clearest example of why community matters. This use case still needs an RF hardware partner, and we don't have one yet. That's not a small gap, and it's exactly the kind of thing a stronger network closes. This is still an open problem for us right now, which is precisely why growing that outreach and community effort isn't optional. It's how we eventually close gaps like this one. That same need, having the right partners in place before we need them, shows up again in our last problem. Bringing us to our fourth problem, dense scientific and regulatory data. Agencies like NASA have to sort through complex science and compliance requirements just to figure out what's even possible before they can evaluate a solution. The real bottleneck is understanding the domain and the paperwork, not the underlying science. We already have a public work in adjacent space and Earth observation AI, so we're really a fit here. And community plays a role here too. Being known in a research community before an RFI even drops is what makes our response feel expected rather than unfamiliar. Staying visible through our events and open community work is what builds that familiarity ahead of time, instead of trying to build it from zero the moment an opportunity appears. And that's really where the pattern across all four of these come in. So let's pull it all together. Every single problem I just walked through has the same recurring gap. We need partners, collaborators, or cleared personnel, and right now we find them reactively, scrambling once a proposal is already in motion. This summer, I helped to rebuild our community platform to fix exactly that. Live calendar sync, so events go live without a developer, self-serve registration and RSVP, admin tools, and a subscribe feature so people can stay connected without any added effort. This isn't just about growing our audience, it's about the infrastructure that lets us build the relationships and partnerships these use cases actually require before we're up against a deadline. Additionally, I spent some time building credibility materials and a consistent process so we can respond to the next problem quickly and consistently. Combined with a stronger community, that means we show up prepared with both the message and the partners already in place instead of building both from scratch. Looking ahead, Anote wants to automate these parts that aren't needed by a person. Some automation includes autonomous outreach to find more people and partners for these exact problems, AI-generated content to stay visible, and AI-assisted drafting so we can respond faster. This goal hasn't changed from everything I just walked through. Make it easier for us to reach people with real problems and easier for them and our partners to stay connected once we do. Thank you.
Awesome. Thanks so much, Alyssa. You did like an amazing job this summer, and you should be really proud. And I have a lot of questions for you, but I'll ask them like offline. And really appreciate your hard work for everything. Yeah.
Sounds good. Thank you.
Thanks, Alyssa. Cheers. Yeah. Hey, Elena.
Hi, how are you?
Doing well. Ready when you are. Yeah.
Okay, thank you so much. How do I share screen?
Yeah, just share screen and then.
Okay, 1 second. Share screen. Yeah, can you see my screen?
Yeah, can you try to make it full screen though?
Okay.
Okay, that's perfect. Yeah, you can get started whenever. Yeah.
Okay. So, okay, I can see. Okay, perfect. 1 second. Sorry. Hi, good evening. So, most discussions about agentic AI focus on the model, but another layer often determines success, the meta decision layer. Before answering, an agent must decide whether to decompose, retrieve, execute code, delegate, or verify. In this work, we introduce an executable benchmark for learning these routing decisions and show that learned meta routing can improve efficiency while maintaining high accuracy. Before an agent can answer a question, it must first decide how to solve it. While some tasks can be answered directly, many require additional reasoning steps such as decomposing a complex problem, retrieving information, executing code, delegating to another specialized component, or verifying the final answer. These operations can be combined into different workflows depending on the task. We call this decision process meta routing. Rather than choosing only a model or tool, the router predicts a sequence of operations that should surround the model call, balancing accuracy, efficiency, and cost. The rest of this presentation focuses on how we learn these routing decisions and evaluate them using an executable benchmark. So what exactly is an executable benchmark? To evaluate meta routing, we developed executable benchmark containing 504 generated tasks across 3 workload families: data analysis, frozen corpus research, and document processing. The dataset is divided into training, development, held-out test, and lexical shift challenge splits. Unlike traditional routing benchmarks that compare predicted routes against annotated labels, every task in our benchmark executes a deterministic workflow and is evaluated using an exact answer checker. As a result of this, success is determined by whether the selected workflow produces the correct final answer rather than whether it matches a predefined route. This allows us to evaluate routing policies in a reproducible and objective way while directly measuring the impact of routing decisions on the task performance. So here you can see the composition of our datasets for training, development, and held-out tests. And a key challenge in evaluating routing policies is separating routing errors from execution errors. If a system fails, we want to know whether the selected workflow was wrong or whether the executor itself produced the wrong result. To isolate the routing policy, we designed every benchmark task so that omitting a required operation changes the final answer. For example, aggregate calculations require decomposition before code execution, multi-hop research questions require both decomposition and retrieval, conflicting evidence requires verification, and retrieval outages require delegation. Because the executor is deterministic, it behaves the same way every time. The only variable is the routing policy and the workflow it selects. This lets us directly attribute success or failure to the routing decision, making the benchmark much more informative than simply evaluating final task accuracy. To learn these routing decisions, we designed a lightweight meta router that takes only the raw task text as an input. Instead of relying on a large controller, it uses simple textual features, including word unigrams, bigrams, for example, 2 words together, and character n-grams to predict which support operations are needed. The predicted probabilities are calibrated on the development set and then greedily composed into a workflow while respecting 2 main constraints: maximum of free support operations and a normalized cost budget based on existing research that we conducted for this project. Finally, the answer step is always appended. This lightweight design allows us to isolate the value of compositional routing, showing that performance gains come from selecting the right sequence of operations rather than from using a more complex routing model. So for this project, we did research from ACL and also NLP conferences to learn that lightweight learn router is one of the most efficient ways to basically focus not just on accuracy but the final quality of the outcome. So to evaluate our approach fairly, we compare it against a diverse set of baselines, including direct answering, random routing, keyword-based rules, static workload routing, and fixed agents that always executes every operation, and an oracle route. Together, these baselines represent progressively stronger routing strategies, from simple heuristics that were mentioned in previous works to idealized upper bounds. However, the most important comparison is learned one-shot router. It uses exactly the same text features, training data, and supervision as our model, but is restricted to selecting only a single support operation. By keeping the representation and learning algorithm fixed, composition becomes the only experimental variable. If our compositional router consistently outperforms the one-shot router, we can attribute the improvement to learning multi-step workflows rather than to a stronger text encoder or a more powerful classifier that normally is done. This controlled comparison isolates the contribution of compositional meta routing and specifically allows us to evaluate what contribution of our project and demonstrates that many tasks require multiple coordinated operations, not just a single routing decision. And we now evaluate the learned router on 108 held out test tasks. Our approach achieves 100% accuracy, and it's not really overfitting. It's more like combined accuracy is 100, but the actual accuracy is around 90, while maintaining a normalized route cost of 1.76, demonstrating that it can select efficient workflows without sacrificing performance. Compared with the strongest static routing policy, it reduces execution cost by 43%, and compared with the learned one-shot router, it improves accuracy by more than 40 percentage points. This result shows that the benefit comes from composing multiple reasoning operations rather than selecting a single action. So when we selected single action, performance was already around 95%. So we were able to increase accuracy by improving and focusing on the meta routing process. This result shows that the benefit comes from composing multiple reasoning operations rather than selecting a single action. By executing only the operations required for each task, the learned router achieves both higher accuracy and lower execution costs and fixed workflows. So here the actual, basically, the outcomes of all the tests. This table summarizes the performance at every routing policy. So we can see that 93.5 accuracy was achieved even when task wording changes. So we were able to just improve the accuracy. The fixed agent is similarly robust. So our approach is specifically in innovating and proposing further improving accuracy and focusing on meta routing process specifically. The fixed agent, for example, is similarly robust, but it pays the highest execution cost because it runs every operation regardless of necessity. All the other end of the spectrum, direct answering and the one-shot router, are inexpensive but fail on many tasks because they cannot compose the multiple operations required for complex reasoning. So here you can see that the actual challenge is in learned budget router. So we are helping to optimize that task and also learned one-shot router, and we're proposing meta routers. Basically, multiple operations will be considered, not just one shot. And if we focus only on one shot, we achieve only around 40% of accuracy. So that was our main contribution to the project. And to test how well the router generalizes, not just on our test dataset, we created a lexical shift challenge where the required operations remain exactly the same, but the task descriptions are rewritten using more distant paraphrases because I was worried about 100% accuracy. So we decided to actually diversify the test cases. As mentioned before, while the learned router performs perfectly on the standard test set, its accuracy drops to 75%, while the static workload router maintains 93.5 accuracy. Importantly, this does not indicate a failure of the executor. When the correct workflow is selected, the executor still produces the correct answer. Instead, the challenge exposes the router's weakest point, predicting the required operations under changes in wording. The most common errors are missing code execution for quantitative tasks, decomposition for multi-hop questions, and verification for conflicting evidence. These findings suggest that future work should focus on improving operation prediction rather than redesigning the execution framework. So it basically shows that it's not necessarily the algorithm itself, it also requires making some changes in the actual test cases in actual texts that we're using and testing our data sets on. So it gives us like inspiration for any future improvements for this work. To understand these failures, we analyzed the incorrect routing decisions in the lexical shift benchmark. The key finding is that the executor is not the source of the errors. When the correct workflow is selected, it consistently produces the correct answer. So the main challenge was predicting the required operations from paraphrase task predictions. We observed three common failure modes. Quantitative paraphrases fail to trigger code execution, multi-hop questions are mistaken for simple retrieval tasks, and changes in conflict-related language cause verification to be omitted. These error patterns point to clear future directions, including richer semantic representations of the actual test cases we test on, broader training templates, and confidence-aware routing. Rather than redesigning the executor, our results suggest that improving operation prediction is the most promising path forward. Finally, we translate all of our experimental results, all of this testing, into practical deployment strategy that we used for our conference submissions. So our evaluation showed that learned routing is highly efficient and performs best on the standard benchmark, while static routing is more robust when tasks wording shifts or the router is uncertain. Rather than choosing between these approaches, we combine them in a hybrid architecture so that we both retain both utility points of both models. A lightweight pre-router first predicts required operations and estimates its confidence while enforcing a cost budget, which was around 75% only accuracy. If confidence is high, the system executes the learned composed workflow, minimizing unnecessary computation. If confidence is low or the input appears to be out of distribution, the system falls back to a predefined static workflow that already hides around 93% accuracy that prioritizes reliability over efficiency. We also retain execution traces for auditing and debugging, making the routing decisions transparent. This confidence-gated architecture preserves the efficiency benefits of learned routing while also maintaining the innovative approach that we introduced in maintaining the robustness required for real-world agentic systems, illustrating how the ideas presented in this work can be integrated into production environments in more practical setting. So the key contribution of this work is a new unit of control. Most existing approaches make a single routing decision, for example, selecting which model to use. And from previous slides, we saw it's only around 40% accuracy if we focus on one-shot model. So how much evidence to retrieve or how to sequence two calls within a workflow. In contrast, meta-routing predicts the workflow itself. Rather than optimizing the individual component, it decides which reasoning and execution operations should be composed to solve a given task. This shifts the focus from optimizing isolated decisions to optimizing the entire reasoning process around the model. During inference, the router first assigns the probability to each support operation based on the task text, estimating how likely each operation is to improve the final answer. Rather than executing every possible operation, it then builds a workflow under two constraints: a maximum free support operations and a normalized root cost budget. To conclude, this work demonstrates that operation-level meta-routing can be evaluated reproducibly using an executable benchmark with deterministic execution and exact answer checking. We also identify the current limitations of our work. So the benchmark uses generated tasks and local components rather than live users or production systems. So we lack actual live user data. So our results should be viewed as a controlled evaluation rather than a deployment study. Looking ahead, we plan to improve robustness through semantic encoders, multilingual and domain shift evaluation, live tool integrations if we have more resources and access to data, and observation condition replanning. Ultimately, our goal is to make the reasoning process around the model measurable, interpretable, and optimizable as the model final output. So yeah, thank you so much for your time.
Thanks so much, Helena. This is an incredible presentation. You should be really, really proud of your work that you did this summer.
Thank you so much. Yeah, and thank you so much for the opportunity to work as an AI fellow. It's my second summer doing it, and I'm so grateful that I'm learning more about machine learning and having an opportunity to work on practical tasks. Yeah, it's my first startup where I'm doing machine learning related practical experience. So yeah, I'm very grateful. Thank you.
Feelings mutual. We're very grateful for your amazing work, and thanks for your time.
Yeah, thank you. Bye.
Is this your presentation, by the way? Can you hear me okay?
Hello?
Hey, can you hear me okay?
Yeah, I can hear you. I'm sorry.
Do you think you can go video on?
Yeah. So I'm so sorry. I missed my train, so I'm just like a little bit behind on like getting ready for this, but I'm
Yeah.
ready to present.
No, if you want, we could just do it yours later tonight. Like we can do like 11 p.m. if that works.
Yes, that's perfect actually. Thank you.
Okay, let's do that then.
Okay, thank
We
you.
can catch your train. Yeah.
All right. Thanks.
Bye. Hey, Yingzi.
Hi,
How are you?
I'm good, thank you. How are you?
Doing really well. Best of luck today. Feel free to share your screen and get started whenever you're ready.
Okay. Oh, can you see my screen?
Yeah, but it's not full screen for some reason.
Oh,
You see what I'm saying? Let me see. Oh yeah, how do we move it to be wider? Give me a second.
well, let me try again.
Okay, that's yeah. Feel free to get started whenever you're ready. Best of luck.
Okay, thank you. Today I'd like to introduce Orchestra Bench, a benchmark we built to evaluate orchestration reliability in multi-agent systems. Most existing benchmarks ask one question: Did the task succeed? We ask a different one. When something goes wrong, what failed? Can the system recover? And how far does the error spread? Orchestra Bench is designed to answer those questions. So, what is actually new about Orchestra Bench? Existing agent benchmarks are very good at measuring whether a task succeeds, but when a real multi-agent pipeline fails, they usually cannot tell you what failed, when the failure started, or how far the error propagated. Those are exactly the questions that matter if we want to understand or improve orchestration. Orchestra Bench changes the unit of evaluation. Instead of only scoring the final answer, we evaluate how the orchestrator behaves after a failure. Specifically, we measure recovery rate, cascade propagation, routing decisions, and decomposition quality. To do that, we built a seed reproducible benchmark with controlled failure injection and evaluated 5 representative failure modes through 4 controlled experiments. The key idea is simple. We're no longer evaluating whether the agent gets the right answer. We are evaluating how reliably the orchestration process behaves when something goes wrong. So, how does Orchestra Bench actually work? The benchmark follows a very simple 4-step process. First, we generate a seed-controlled workflow. Second, we inject one known failure at a specific stage. Because the injected failure is controlled, we always know exactly what failed and where it started. Next, we execute the workflow under different orchestration policies. And finally, we measure what happens downstream, including recovery rate, cascade propagation, and decomposition fidelity. For the experiments I'll show today, we inject 5 representative failure modes at the prompt level, ranging from explicit tool invocation errors to more subtle semantic failures, such as context pollution and conflicting outputs. The key advantage of this design is that every failure has a known source, so downstream behavior can be measured objectively instead of inferred after the fact. Now let's start with routing. This is the simplest experiment, but it reveals an important insight. The question we asked is straightforward. Does the router actually understand the task, or is it simply matching surface cues? We constructed 26 gold labeled routing cases. 16 are aligned, where the surface flags match the task intent, and 10 are adversarial, where those surface cues become misleading while the intended routing remains unambiguous. Now look at the middle of the chart. The heuristic router performs perfectly on the aligned cases, but drops to 0% of the adversarial ones. In contrast, both the TF-IDF router and the LLM router recover every adversarial case. The key difference is not model complexity, it's that they actually read the task description instead of relying on predefined flags. Finally, notice the fixed baseline on the left. Even without understanding the task, it still achieves 20% on the adversarial cases. The heuristic router performs even worse, showing that misleading signals can be more harmful than having no signal at all. So routing tells us whether failures are recognized correctly. The next question is what happens after a failure occurs? We used the same controlled failure injection setup, but this time we asked a different question. After a failure is introduced, can the system still recover? The answer is surprisingly clear. The 5 failure modes naturally fall into 3 recovery tiers. At the top, 2 invocation errors recover almost perfectly. Because the failure is explicit, the agent recognizes it and simply recomputes the missing step. Next comes ambiguous delegation. It succeeds about 30% of the time. The intent can sometimes be inferred correctly, but recovery is no longer guaranteed. The remaining 3 failure modes, context pollution, conflicting outputs, and premature action, never recover in our experiments. Once an incorrect latent state enters the workflow, it continues propagating through the rest of the pipeline. We also evaluated a retry policy. Retry improves none of these latent failures. If the internal state has already become corrupted, repeating the same execution simply reproduces the same mistake instead of repairing it. This suggests that reliable orchestration depends less on retrying failures and more on detecting and attributing them before they spread. A natural question is whether this recovery pattern is specific to our experimental setup. We tested that in 2 ways. First, look at the chart on the left. We kept the underlying computation exactly the same, but reframed it as a loan approval workflow instead of an arithmetic task. The exact recovery rates changed. Tool failures dropped from 1 to 0.7, while ambiguous delegation increased from 0.3 to 0.4. However, the overall recovery pattern remained unchanged. Tool failures were still the most recoverable, ambiguous delegation remained only partially recoverable, and latent semantic failures still failed consistently. Next, look at the table on the right. We repeated the same experiments across Cloud Sonnet, Opus, and Haiku. Again, the exact numbers vary across models, especially for the partially recoverable cases, but overall ordering remains remarkably consistent. True failures remain highly recoverable, while latent semantic failures remain difficult to recover across all three models. Taken together, these two robustness checks suggest that the recovery pattern is not tied to one specific task framing or one particular model. The exact percentages change, but the relative behavior remains stable. The previous experiment tells us whether a failure can recover. This one asks a different question. If it cannot recover, how much damage does it cause? We injected a single failure at the beginning of the workflow and gradually increased the pipeline depth from 3 to 7 stages. We then measured the cascade radius, the number of downstream stages that become corrupted. The result is very straightforward. True failures remain flat at zero. Even as the workflow becomes deeper, they stay locally contained because the failure is detected immediately and repaired before it propagates. Latent semantic failures behave very differently. Their cascade radius grows almost linearly with pipeline depth, about 0.9 additional corrupted stage for every stage we add. In other words, the deeper the workflow, the more opportunities a latent error has to spread. One important caveat is that this experiment uses a controlled dependency chain, so some increase with steps is expected by construction. However, the contrast between contained tool failures and propagating latent failures remains consistent with the recovery results from the previous experiment. The final experiment asks a different question. Can two systems produce the same answer, but with very different orchestration quality? We compared two execution strategies on the same set of tasks. One solves the problem monolithically, while the other explicitly decomposes it into smaller subtasks. We then evaluate how closely that decomposition matches the goal workflow. The planner achieves perfect decomposition fidelity, while the monolithic policy scores only 0.37. More importantly, both systems still achieve exactly the same final task accuracy. If we evaluated only the final answer, these two systems would appear identical, but from an orchestration perspective, they're very different. The planner produces an explicit structure that can later be delegated, audited, and recovered from, whereas the monolithic solution exposes none of that internal organization. This illustrates why task accuracy alone is not enough to evaluate orchestration quality. Three things I'd like to work out with. First is orchestra bench measures orchestration reliability rather than one final task success. How systems root, recover, and decompose with everything seed reproducible. Second, failure modes are not interchangeable. True faults recover, ambiguity partially recovers, latent semantic faults essentially never do. If you are designing an orchestrator, that distinction should drive your architecture. Third, and this is the practical one, blind retry is not a containment strategy. It reproduces latent faults and delays detection. What these systems actually need is failure attribution, state repair, and cascade containment. These are controlled mechanisms proposed on a verifiable chain, single agent with prompt level injection. Full multi-domain and real multi-agent validation is future work. Thank you all. I'm happy to take questions.
Hi, Yingzi. Thanks so much. This is like a really amazing presentation. You should be like really proud of your work that you did this summer. I thought it was fantastic, and I really appreciate all your hard work.
Thank you.
Yeah, I have some questions, but I'll send them to you offline. And thanks so much for your time. Yeah.
Thank you.
Hey, Bjorn. How are you doing?
I'm doing good. How are you?
Doing good. Yeah, so feel free to share your screen and take over when you're ready.
Oh, okay. Yeah, so I will be talking about how Anote AI is deploying the products, and I'm leading the charge in this deployment phase of like DevOps and securing the environment for production product and the dashboard and stuff like that. So first of all, when a code piece upload basically push to the GitHub, it will uh, first go to PR pull request, and then if everything checks out, it will push to the dev branch um, where a CI/CD pipeline will run, basically testing out everything from code quality, integration testing, and after that is completed, it will be pushed to main branch. Basically, is a production branch. That means it will run the test again, and then it will run the EC2 deployment for backend and S3 and CloudFront for the front end deployment using CI/CD. So all the NO product are containerized, meaning that it uses Docker in the production environment on AWS, and we use EC2 instance to deploy all the backend infrastructure that NO have. So for as I mentioned before, front end is deployed on S3 bucket and using CloudFront to like validate and invalidate previous sessions and resources. I will then also addition to that, there's monitoring like using CloudWatch to monitor the activity, like if it's increasing or decreasing. I would then right now will show the production ready product. So far, I so far two of the annual product are already in deployment. One is Panacea. It's basically a autonomous intelligent platform. Like think about cloud and whatnot. Like you can generate basic chat with AI chatbot and using RAG. So if I sign in, as you can see, you can create a new chat. Let's say hello. It will respond to you, and addition to that, you can upload a profile picture. You can bring your own API like Anthropic, OpenAI, Google, and in future there will be more providers. In addition to that, you can keep track of recent activities right here. Also, the buildings and the dark mode and light mode features. So moving on to Anote product. So basically, this product help with like labeling and training and evaluating models. You can see right here. So for the GitHub, the CI/CD pipeline, it's basically let me show. It's basically it's basically a workflow that runs So yeah, so right here, so first step is building and pushing the image to ECR registry on AWS. So using AWS credential to log in, and for deployment, we're using AWS credential via OIDC. It's more secure than SSH. And for uploading to the for getting the image to the EC2 instance, we're using SSM session manager. So instead of using SSH, it's more secure for both way communication between registry and EC2 instance. And that's basically it.
Thanks, Biron. Could you quickly just show how the products work, I guess?
Huh?
I know you kind of talked a little bit about the chatbot, but do you want to show like how the products work a bit?
I'm not sure what does the end product, the dashboard is. I don't think
It's okay. Honestly, yeah, you did a great job. So thanks so much for your time, Birong, and I'll be in touch soon. Yeah,
Thank you.
really
Bye.
appreciate your hard work. Yeah,
See ya.
see ya. Hey, Brian.
Hello.
Good.
How are you?
Doing well. Yeah, feel free to share your screen and get started whenever you're ready. Yeah.
Yeah, sure. Can you see the screen?
Can you try to go full screen? Yeah, hit slideshow button. Okay, yeah, you should be good to go. Yeah.
All right. Yeah. Hi, everyone. This is Brian. And I'm going to talk about the paper named Beyond Pass at K, Measuring Reliability and Security of Agentic Code Generation. It's conducted by me and Sharon. So in this presentation, I'll focus mainly on the second half of our study, including security-adjusted metrics, bench, pilot limitations, and future work. So before everything started, I just want to briefly establish the central problem. So current coding agent benchmarks can overstate performance because some implementations misuse PassFK. So instead of using independent agent attempts as samples of unit tests with a single unit dependent rollout. So we propose reliability at K, which measures success across repeated independent agent runs. So using our synthetic code bench experiment, we found three things. So first, identical test pass rates can receive different scores purely because of the test suite site. And secondly, the broken metric reports nearly perfect scores, while corrected reliability is actually very low. And third, a cheap single run proxy is not accurate enough to replace repeated evaluation. So the first half of the paper shows that passing many tests is not the same as reliably solving a task. So I'll be moved to the next question. Even if the code works, is it also secure? So now we're at the functional reliability of security side of the paper. So H4 asks whether adjusting reliability security changes agent scores or rankings. So we introduce a security adjusted reliability at K. Under this metric, we roll out count, as successful only when it clears two gates. Gate 1 is functional correctness. The generated solution has to pass the required test. And gate 2 is security screening. The code must also pass the security scanner. If either gate fails, the rollout does not count as a secure success. This distinction matters because a solution can satisfy its functional specification while introducing dangerous behavior. A normal benchmark may reward that solution because the output passed tests, but the security adjusted metric is designed to reject it. So the pilot scanner searches for several high risk patterns. These checks are intentionally simple. They are not presented as a complete vulnerability analysis. They create a first operational test of whether functional reliability and security aware reliability can diverge. A live API experiment contains 240 generations, 3 agent profiles, 10 tasks, and 8 rollouts for each task agent pair. And 5 tasks are security sensitive, meaning that unsafe implementations are plausible and should activate the scanner. Agent acts and cloud code are used, and they use the same underlying cloud model. Their difference is more likely caused by system prompts or agent framing than by model capacity. Codex uses GPT-4o, so this experiment is not intended as a product model leaderboard. It's purpose to test the behavior of the purpose metric. So this is the result of H4. So in the pilot, reliability at 5 and security adjusted reliability at 5 were identical for all 3 agents. Kendall's taught was 1.0 with a p-value of 0.333. And because the adjustment did not change the ranking, H4 is not confirmed. But we need to interpret this result carefully because the conclusion is that this particular pilot did not generate enough separation for the security adjustment to bind. So in other words, the security gate was present, but under the current test status, scanner and cutoff, it did not remove enough otherwise success rollout to change the final order. A negative conclusion would claim that security adjustment has no value, but the experiment only shows that this small pilot is underpowered for a decisive rank level test. So I'll say this is inconclusive instead of a negative result. In our H4, we have 4 design constraints. So first of all, the experiment included only 3 agents, which gives very limited statistical power. And secondly, security cutoff is 0.8, which is relatively lenient. A rollout could trigger 1 of the 7 pattern checks and still clear the threshold. That reduces the chance that the security gate changes whether a rollout counts. And thirdly, only 5 out of 10 tasks are security sensitive. The other half of the corpus may test functionality, but does not meaningfully stress the scanner. And it dilutes the effect of the security adjustment across the full benchmark. And lastly, the scanner contains only 7 heuristic pattern checks. Pattern matching can identify obvious risky constructs, but it is not equivalent to a complete security audit. These limitations mean that the unchanged ranking does not show that the agents are equally secure. It only shows that this scanner task threshold combination did not distinguish them. For a broader takeaway is that security adjusted reliability remains a very useful metric, but it needs to be tested with more agents, harder security tasks, stricter threshold, or severity weighted scoring. And then we add a small real world reliability test, reality check by using the Sweet Bench Verified. So this pilot is important because from H1 to H3, all of them are synthetic stress tests, while Sweet Bench evaluates repository level software engineering tasks. The pilot uses 5 verified tasks, 1 agent, and only 1 attempt per task. And the setup also includes leakage checks. The agent does not receive a gold patch or a hidden test. So in addition, all 5 submitted patches are non-empty and apply cleanly. And this means the unresolved tasks are not simply infrastructure failure or invalid patches. They fail because modified repository does not satisfy the full hidden evaluation. And the strict result is 1 resolved task out of 5, giving a reliability at 1 of 0.20. However, the macro average hidden test pass rate is 0.8049, and the macro average regression rate is 0.1539. And this gap is the main finding. Hiding test pass rate above 0.80 sounds pretty strong, but the task level solve rate is only 0.2. Partial test performance can hide difference between a near miss and a complete solution. And individual failure modes make this concrete. So some patches fix part of the requested behavior, but miss required changes. And others introduce regressions in the tests that previously passed. A benchmark that only summarizes the portion of passing tests can give substantial credit to these incomplete or harmful solutions. This pilot is too small to validate multi-rollout reliability in Sweet Bench, but it still supports the paper's diagnosis concern, which is partial test pass metrics can materially overstate task level success in a real repository. So we now have some limitations here, and this paper should be read as a methodological demonstration, not as a final product leaderboard or not as a security certification. So firstly, from H1 to 3 is synthetic. Their strength is control. They clearly expose the estimator error and quantify its effects. Their limitation is externally validity. They do not establish the performance of real commercial agents. Secondly, H4 is underpowered. It concludes only 3 profiles, 1 security cutoff, and a small heuristic scanner. So it cannot support a strong conclusion about whether security adjustment changes rankings in general. And thirdly, the Sweet Bench pilot is pretty narrow. They only have 5 tasks, 1 repository, 1 agent, and only 1 attempt per task. It provides a reality check, but it cannot estimate reality at 3 or liability at 3 or liability at 5, because those metrics require repeated independent attempts. And fourth is that the pattern-based security screening is not a full security audit. It can catch obvious high-risk constructs, but it does not measure all vulnerability classes or exploit severity. And there's also an accept edits constraint. So agent can modify files, but cannot run shell commands or execute tests during its attempts. And this may differ from a fully interactive agent workflow, and the official harness still standardizes the external evaluation, but the restriction may affect the type of solutions the agent produces. So in conclusion, the main contribution of this paper is methodological. So first of all, pass at K should not use unit test counts as a substitute for independent agent attempts. Secondly, reliability should be measured across repeated rollouts by using reliability at K. And thirdly, functional correctness alone is not enough. A strong evaluation should also consider whether the generated code is secure. The sweet bench pilot reinforces the point, which is an agent can pass a large percentage of tasks while still failing to fully resolve the task. And future work should expand agent pool, test stricter security thresholds, use severity weighted security scoring, validate the metric in real vulnerability dataset, and run repeated attempts across more sweet bench repositories. And the final message of the paper is that passing many tests is not the same as reliably solving the task. And solving the task is not the same as producing safe code. And that concludes my presentation. Thank you so much.
Hey, Brian, thanks so much for doing a really awesome job this summer. And
Yeah,
yeah, you should
thank
be
you so
really
much too.
great job. And I guess we'll see you at the summer party Friday.
I'll be there. I'll be there.
Okay. So yeah, I'll see you then. And then thanks a bunch for your hard work and really appreciate it. Yeah.
Yeah, thank you so much.
Yeah. Cheers.
Bye.
Hi.
Hey, Henry. How are you?
I'm great. How are you?
Doing well, doing well. Yeah, feel free to share your screen and get started whenever you're ready.
Yeah, of course. Oh, can you see the screen? Oh my god. I will change that. Sorry. Can you see the screen?
Try sharing it again. I saw it before, right in the beginning, but
I mean it's not working for. I will just quit and join again.
yeah, perfect. Sounds good. Okay, awesome. Yeah, I'll try now, I guess.
Should I? I'm trying to click the replace, but it was not working.
Just try hitting the share screen button on the restream.
Yeah, I clicked that and it's not working. I will just share the whole monitor could work, I guess.
Yeah, that's fine. You can share the whole monitor. Yeah.
Yeah, I will.
Okay, awesome. Yeah, one more try.
Yeah, I clicked to share the whole screen, but it's still, I don't know why it's still not working.
What about the H button? Can you press H?
Yeah, I'm pressing H, but it's not interacting.
Um,
And I click the replace button, but it's not working.
what if you try unsharing your screen and then share it again?
Yeah, I
Whatever.
clicked the stop one, but it's still, I don't know,
Let
like
me
what happened.
unhide you and then I'll hide you. Try again.
Yeah, sure.
Okay. And, do you not see like there's a share screen like on the bottom for you?
Yeah. At first, it seems worked, but I don't know. It's just, yeah.
Maybe try going in from like a separate browser really quickly.
Oh, yeah, that's a great idea.
Yeah.
Hi. I'm using the Firefox now.
Okay. Can you hit this share screen?
So I tried. Oh, I think there are probably some privacy issue. It it asks me to enter my password.
Okay.
So maybe I have to join again. Sorry.
Okay.
Yeah, I hope this time gonna work.
Let's see. Worst case, I can share my screen for you. Yeah.
Oh, can you see my screen now?
Yeah, I can.
Is that
Okay.
working now?
Yeah, that works. That works perfectly.
Okay, cool.
Feel free.
So should I just start it?
Yeah, you can get started
Yeah.
whenever you're ready.
Hi. I'm gonna introduce our project. It is called the Retrieval Bench, which is a benchmark work that measures the retrieval knobs user actually turn. And my section covers how chunking and embedding choice change the retrieval quality across domains, plus one deployment budget result. So before I show the result, let me explain our motivation for our research. So why chunking is so important? Actually, every rack system lives or dies by retrieval. The module can't answer from what retrieval didn't bring back. So naturally, there's a huge amount of attention on retrieval quality, but almost all of it goes to one knob, which is embedding module to use. And there are leaderboard for that. Uh, and then here's the problem. Like those leaderboard, like BIR or MTB, evaluates on corpora that comes pre-segmented and they score quality only. But before any embedding happens in a real system, someone chopped the documents into chunks, usually with a library default, and that choice is invisible to every benchmark. And because it was never measured, practice runs on folklore. And for example, the DPR used 100 word passages in 2020, and that hardened into a convention across the field. Not because anyone showed it was right, but because nobody checked. So our question is simple. If we promote chunking to our first class experimental variable, sync footing as the embedder, how much does it actually move retrieval quality? And is the answer the same everywhere, or does it depend on your domain? And I will show the answer next 10 minutes. And a spoiler here is in 5 of our 12 domains, the chunker you pick matters more than the embedder. So yeah, to answer our question, we need breadth. So the matrix spans 12 domains from public collection, and the way to read this slide is from left to right. So from the law documents to short ones. At one end, the full-length text, biomedical papers from try-COVID, financial polls, Australian court decisions, argumentative essays, and in the middle, the Wikipedia, drive task and natural question, entity retrieval, fact checking, multi-hop QA, and at the other end, the corpora that are already short, the medical and the scientific, abstract, and the quora, where each document is a single question. The quora is our built-in control. Documents so short that chunking shouldn't matter, which let us check that our pipeline doesn't manufacture effects. I will come back to that. And for cross-domain comparability, every corpus uses the same sub-sampling policy, 2,000 filter documents plus every relevant one. And here is what field grade. There are like 4 retriever. The BM25 as the Spurs baseline, plus 3 dense embedders. The OpenAI's small API module, and 2 open source 33 million parameter modules, and 4 chunking strategies. The fixed 512 token windows, which is the industry default sentence windows, recursive splitting, and semantic merging. One setting per family. We compare strategies, not to hyperparameters. One design detail that worthy to be mentioned here is the retrieval runs over chunks, but the scoring is at the document level. So each document appears once, scored by its best chunk. So a chunker cannot win just by producing more pieces. When chunkers differ, segmentation generally change what the retriever could find. And yeah, running everything against everything give us a total 192 scored conditions, but the real instrument is what we compute per domain. So take one domain grade, the chunkers as rows, and the 3 dense embedders as columns, and NDCG score in each cell. There's two-way Anote ask one question of the variance across those 12 cells, like how much come from moving along the rows, changing the chunker versus the columns, changing the embedder. So those two shares are CSI and ESI. They sum to 1 together with an interaction term. And the reading here is simple. If CSI beats ESI in one domain, then the chunker you pick moves quality more than an embedder you pick. Uh, the the BM25 is scored in the full grid, but stay out of this decomposition. It is the lexical baseline, not part of the chunker versus embedder questions. So for findings, the finding one is how much does the chunking move quality? The answer is up to 47%. So the biggest win is biomedical was BM25. Around 0.476 was the semantic chunker, and 0.7 was fixed 512 token windows. Nothing else changed. The same corpus, same retriever, same queries, only how we cut the documents. And it's not like a BM25 Kirk. On finance with the OpenAI embedder, the same switch moves quality 26%, and the pattern replicates under the both open source embedder at around 40%. So this is a property of the corpus, not of one system. So the takeaway here is treating chunking as fixed preprocessing can bias a system comparison by nearly half of measured quality. So it is a first class variable. So, as we know, the chunking matters. Should everyone just switch to a fixed 512? The answer is no. That's our finding too. Like, there's no universal winner. So, the best strategy changed with the domain, and it also changed with the retriever. Windows chunking, for instance, help dense model more than BM25 on long documents. And in 3 domains, the two choices generally interact, where the interaction terms explain up to nearly 40% of the variance. And there, you cannot even pick a chunker without knowing which embedder is paired with. In the other 8 domains, the effects are additive, which is itself useful to the two knobs independently. So, and here is our core result, the decomposition for all 12 domains. In 502, the chunker move quality more than the embedder. And I look at which 5, the biomedical, finance, argumentation, and legal. So the long-term structured corpora. In biomedical, trunking explain 82% of the variance, and the embedder only 14%. At the other extreme medical abstract, embedder have like 94%, and trunking only have 2. So for short passages, embedder really is the decision that matters. The standard leaderboard-driven approach works fine there, and this is stable. We run the home matrix and the two more query seeds, and ordering held in 11 of 12 domains. The only flip is the domain we already flagged as the borderline. So for or fanning for is our sanity check. The core documents are single question. There's nothing to chunk, and indeed, all four chunkers land within 2000s of a point of each other. And on every retriever, if our pipeline manufacture effects, they will show up there. And the answer is they don't. So like better still, sensitivity skills was document length essentially 0 on single question, around 10% on case law tags, up to 37 on long biomedical documents. And that's a like those response pattern exactly what you expect if the effect is real. So our last finding, and it's a framing one. We are not claiming finance is a chunking domain as a permanent fact. Like CSI and ESI describe this configuration. Swap in different embedders and the numbers will move. Or on pool probably just inflates embedder sensitivity since it makes small open source modules with a strong API module. But that's exactly the point. This isn't a lookup table, it's a diagnostic you run on your own stack, and it tells you which knob to tune first. So there's one deployment variable, briefly the latency. So quality only evaluation says add a re-ranker. On finance, it lifts BM25 from 0.16 to nearly 0.2, but re-rankers cost time. Under a 200 millisecond budget or latency discounted metric drops that pipeline to 0.133 below the plain BM25. So the ranking of the system isn't a property of the system alone. It is a property of system plus your budget. So relax the budget to 500 millisecond and the re-ranker wins again. So same things as chunking. The deployment variable changed the conclusion. And for limitation, we have like 5 on the slide, but I want to say like 2 are pretty important. First is the embedder pool mixes capacity tires. 2 small open source modules against a strong API module, which likely inflates embedder sensitivity. And the second is each chunker runs at one hyperparameter setting, so our claims are about strategy families not tuned optimal. So to conclude, chunking moves retrieval quality by up to 47%. Is the first class variable, and evaluation that freezes are measuring the wrong thing. Whether it matters more than your embedder is decided per domain. It wins in 5 of or 12, concentrated in long-term structured tasks, and that pattern is stable and receding. So the practical rule is if your corpus is long-term or structured, tune chunking before you shop for embedder. And if it is short passages, then the leaderboard already have you covered. So like in one line, test your checker like test your embedder. That's it. Thank you.
Awesome. Thanks so much, Zuri. Really appreciate your really hard work this summer. You did an amazing job, and you should be really proud.
Thank you, Nathan.
Yeah, I do have a few questions. I'll send you offline, and thanks so much for your time. Yeah.
Thank you.
Hey, Sindhu. Wait, can you say something again? I couldn't hear you.
Can you hear me now?
Yeah, I can hear you
Yeah,
now.
okay, good. Should
Oh,
should I share my screen?
By the way, I think your background's a little bright. I don't know if.
Oh, sure. Wait. Let me give me a second. Let me like move over a second. Maybe. Yeah. Okay, is this better?
Yeah, much better.
Yeah, okay, that's good.
Okay, feel free to share your screen and we can get started. Yeah.
Okay. Give me 1 second. I just want to set a timer.
Yeah, whenever you're ready.
Okay. Yeah, so this is my project, which is the cross-lingual transfer in Thulu legal comprehension. Okay, so I'll just start. Okay, so the problem is that a lot of models are trained in high rhesus languages, right? And those are like models, or those are languages where there's an extensive literary history and the means of training models on that literary history. Most of the world doesn't actually speak in a high rhesus language. And on top of that, especially at administrative processes and legal processes, people don't use those high rhesus languages. So how could a model understand any work being done in those places? For example, in the Indian state of Karnataka, people speak the language Kannada, and that's used in legal proceedings, in the courts, etc. But a secondary issue exists, is that people under these administrative regions often speak a completely different language, unrelated from the administrative language, and a lower resource than the administrative language, right? And so in a lot of regions of the Karnataka state, people speak the language Tulu, which is not represented in administrative processes, and people have to switch to a different language to get their legal needs heard. So how do we address this gap, right? So the question is, can minimal priming and Kannada legal papers alone let a model interpret complaints written in a language that it has never seen? And in that case, when I break down this question, it's that given queries or legal complaints in the Tulu language, can we give essentially small hints of the Tulu language and also use Kannada legal papers as a basis for models to reason and correctly categorize complaints? We don't want to build like a fully working large language model, but instead we just want to understand how comprehension works in these cross-lingual domains, and we're using the legal area as a really good place to ground this as an actual use that would be real life applicable. So the related work, one of the most important areas is context memory conflict, which is that when models have their own internal understanding of a situation, and external information can often sway how they process information after that. They can often defer to conflicted information, even if it's wrong. And Llama 3 is especially notorious of doing this. And related to that is RAG degradation, which is although RAG often helps the model, it can also hurt if it's noisy or when a model has to heavily depend on it, such as in low resource domains, where it doesn't really have a basis of its own and has to go off external information. And finally is the Tulu Kannada bridge, which is it's beginning to be used in the LLM field due to the fact of the extensive history between the two languages, and that is a really good grounded area of understanding multilingual transfer, and that there's already some preliminary evidence that large language models do parse Tulu as Kannada. So this would be it's actually a very grounded experiment, right? Okay, so the methodology. So we wrote 60 Tulu complaints and used 18 Kannada court documents. So these are court documents written in Kannada script and often from lower courts. And then we used 4 query scripts. So for when we wrote the 60 complaints, we wrote them in 4 different scripts, which was Latin script, Kannada script, Tamil, and Malayalam. So the last 3 are all Dravidian languages, which is the same language family that Tulu falls under. And then the last we used 3 models, which was Llama 3, Hexon, and Sarvam. Llama 3 is not trained in Kannada at all, but it has multilingual capabilities. Meanwhile, Hexon and Sarvam are actually Indic models, so they are trained in Kannada extensively, but none of them are trained in Tulu. So the first step to make sure the experiment ran well was cleaning up the corpus, and a lot of the old documents were written in a different, essentially script. So we had to rewrite them in a computer script, essentially. So we had to rewrite them so that the Kannada Unicode was able to be used by the models. And then we had to type them with list categories. And a list category is essentially just a taxonomy for classifying legal situations. And we also use the list categories to classify every single complaint that we had written. And then the second was retrieval. So we had to, for the retrieval pipeline, we broke down all the documents into 800 character chunks and then embedded them along with the query sentences using multilingual E5 large instruct, which is an embedding model. And this is really useful because otherwise, since Tulu and Kannada are different languages, this multilingual model will be able to more accurately parse them. And then to ensure that we got the most accurate retrieved documents, we would use a cosine similarity to compare against court documents and the embedded sentence. And whichever one had the highest cosine similarity, we pick the top 3. We also, for the classification side, so this is how the model classified sentences, there were 3 aspects. The first was the primary, secondary, and tertiary. So the model could have 3 guesses, the primary one, which was essentially the main one, and then 2 other guesses, which were separate categories that it could ascribe to. The second was that we also asked for a reasoning trace verification. So it had to give a reason for why it chose the primary category. And then finally, we had a hits at 1 and hits at 3 score. So the hits at 1 score is if the model's primary guess also matched what we put as the primary category for the sentence, then that was a hits at 1 score. A hits at 3 score meant if the model didn't guess the primary category, but it was able to guess any of the secondary categories that we might have put for the sentence, then that was a hits at 3 score. And for diagnostics, how we would test and understand how the model comprehended the sentences. So we would also look at the trace verification, but also use statistical tests such as denominator checks and Fisher's exact test. Okay, so for the experimental design, we had 13 conditions, which were based across 3 axes. The first was understanding how script played a role in model comprehension. So again, that was the 4 scripts, which is again, Latin script, Kannada script, Tamil script, and Malayalam script. The second was priming. How would priming affect a model? And what I mean by priming is we would only give essentially a small little paragraph explaining the Tulu language with grammar and some basic words. And then finally, we would ask how RAG passages, how the inclusion of RAG and legal papers affected model performance. The priming itself could be broken down into 2 tiers. So every model which had priming had 2 types of priming. The first was just sparse priming. So that would be basic words like to go, to know. But then the extensive priming would give more detailed, would add on to that by giving more detailed words like how would it, like to like a court or to sign or a will, which would kind of give away the sentence. So what we're trying to see is how much priming is necessary for a model to understand language it has no basis in. And finally, we also had a few baselines so that we would use as essentially controls. So the first is the English translation one, and that was isolating how well a model performed when we give a high resource language in the query script, and this was isolating how simply how a low resource document, a RAG retrieved document, would affect that understanding. The second was the Romanized Tulu and Kannada script without any priming and RAG at all. And this was isolating the internal or latent understanding a model might have in the low resource language. Okay, so on to the findings. The first one, which was really surprising, was that comprehension actually transfers without RAG at all. And that's that all 3 models were able to display a significant amount of comprehension in the low resource language that, again, that they had no that they had no training in without having major priming or RAG retrieved documents at all. And we also wanted to make sure this was just above chance. So we checked against random guessing and also majority class, which would be like if a model gets just the most common category in the entire complaints data set, and it beat both of them by a huge percentage. So the models were actually able to have this understanding the language. And but the really important thing to know is that this is only comparable in Kannada script. And when we use the Romanized script or we use Tamil and Malayalam, it didn't reach this level. So script is really important for a model to understand based on, and this is like reflecting previous findings by other people. And the second is we also checked against reasoning trace to see how the model comprehended. And for example, for Sarvam in condition H, which is again, no priming and no RAG, it was correctly able to identify the word court and then use that as a basis for reasoning, which again, we didn't teach at all. And then with sparse priming, it actually did help somewhat with Llama 3 and Hex 1, although not significantly, and actually did affect Sarvam negatively. So what we're trying to say is that there actually is latent understanding in models, even without any data, without any training. Okay, and second is that RAG collapses Llama 3. So to understand the picture, we have to first talk about Sarvam and Hex 1. And Sarvam and Hex 1, they were able to they're not able to fully understand, but what they were able to maintain their accuracy scores given retrieved documents. and so it's like if they were given just if they were given just priming, they were able to maintain that same score with RAG and priming. Meanwhile, Llama 3 its performance collapsed under RAG, and it's like you can see here with with full priming and RAG, it had a really low score, and that's reflective of it if it just only had RAG. These are like really similar scores, meaning that when we gave priming, it didn't really matter if we also gave RAG, and it deferred to the documents over its own understanding. But it does have a strong understanding, given that this really high score with just priming and no RAG at all. And then also query language is really important, and I'll get to that in the next slide. Okay, so when RAG failed, how did it fail? So there were two separate mechanisms on how it could fail, which were across all three models, but specifically it was really common with Llama 3. And the first is fact substitution, which is at a really like small but often wrong detail, but it could be a maybe marginally related to the query, but it wasn't really, right? And that would be actually included into the query and baked into it. And this new modified query was used as a basis for reasoning, and then obviously the model got it wrong. The second was confabulation, which is that the model would find a reason that existed neither in corpus nor query and use it again as a basis for reasoning and got it wrong. We also wanted to make sure that this wasn't due to label ablation. So because we would give the model, like along with the passage, we would give what label that passage fell under. So we removed that, but that didn't significantly affect model performance in Llama 3. And that we also wanted to check whether RAG ever helped Llama 3, and it really didn't. And we finally, to check if there's any way as a preliminary mitigation step, we use a CRAG judge layer. And what this is, before any of the documents reach the call of the Llama 3, we added a second column, which would independently verify every single passage retrieved and see if that was relevant to the query. And this is actually really interesting, because when the query was written in Kannada, it didn't help. But when it was written with an English translation, the model was actually able to start forming some form of discernment and accurately classified between or it didn't accurately classify, but it was able to classify at all. And when it was in Kannada script, it wasn't. So this is really important, because what we're saying is that a high resource language does give Llama 3 a scaffold to use and then to operate in a low resource domain, which may have already existed with Sarvam and Hex1. Okay, and finally, when I was talking about latent knowledge and RAG robustness, you would think those are like two separate things, but they're really not. With Hex1 and Sarvam, they had high performance with Kannada script, right? Which was already established as really important for a model to gain any form of understanding. And when we had written the queries in a Romanized script, then performance heavily failed in both Hex1 and Sarvam. But they were able to maintain RAG robustness under Kannada script and priming and RAG. So what's important is that they were able to that the script performance affected them, but only when it was in English in a Latin script. Meanwhile, with Llama 3, when it failed with the Kannada script and RAG, it had similar scores as to if it had the Romanization script. And what I'm trying to say with this is that the RAG robustness and script advantage, they're related to each other. If a model is able to perform well under RAG, it probably is also able to maintain the script advantage that Kannada provides. But if it fails under RAG, then the script advantage disappears and it doesn't help the model anymore. Okay, so the conclusion is, so if there's anything to take away, it's that models actually do exhibit latent comprehension in low resource languages without any training. And this may be due to the fact that they already have training in a related language, or they exhibit multilingual abilities and are able to apply this to new languages. The second is that script is the lever. If we want to have models operate in low resource domains, we need to understand what scripts help them perform more accurately under such circumstances. And it seems that Kannada script, which is more lexically similar to Tulu than any other language, is very useful in that manner, and maybe this can be applied across all the other language pairs. And finally, that RAG is a liability, but it's heavily model dependent. If a model is trained in the language of the RAG corpus, then it's able to maintain the robustness even in a more confusing domain. But if it's not, then it needs a higher resource language to kind of anchor itself. For implications in future work is that something that's really important is that how a model performs with an unfamiliar corpus is actually not as dependent on the corpus as it is on how the model parses it. And second is that the evaluation methods used, such as reasoning trace and statistical honesty, seem to be viable and useful in other domains in these multilingual areas. And finally, if any future work wants to be done, it's probably going to be done with Dravidian transfer, so in the whole Dravidian family, larger data sets and stronger mitigation to understand if this effect is applicable across larger domains, and if there's any way to mitigate these effects. And finally, what would be really exciting if we can find any language pairs that, again, reflect these similar circumstances. But that's it. So thank you.
Amazing. Thank you so much, Sindhu. This is a really insightful presentation.
Yeah, of course, Ajahn. Thank you.
You should be really proud, and thanks for doing a great job on this. So.
Yeah, of course. Okay, thank you. Bye-bye.
Yeah. Hey, Emily.
Hi, how are you?
Doing well, just been learning a lot today. Yeah, I guess feel free to kind of get started whenever you're ready. So yeah.
Okay, cool. Is this fine?
Yeah, that looks perfect. Yeah.
Okay, cool. All right. So yeah, my name's Amelie and I worked on this posture and sustainment optimization under adversarial uncertainty paper with Alyssa Lee. But so basically our work is about a decision that planners need to make before a conflict starts. So where do you put your assets and if you don't know what your adversary is going to do? So this specifically is a pre-commitment layer. So it sits right below mission scheduling and sensor tasking. So it's really important to get this right because a bad commitment here cannot be fixed later down the line. So the limits of current planning is that the current common practice at least, is a greedy heuristic, which ranks locations by value and pours the most resources into the highest value bases. It's pretty simple and easy to read, but that also means it's really predictable for your enemy. So these predictable deployments can cause irreversible commitments that will later on be expensive in both time and money to fix if you even have the time to do so. So our research question is straightforward. Can scenario-aware optimization produce more resilient posture decisions under uncertainty compared to the greedy default? So what we looked at first was optimizing across different futures. So traditional planning just optimizes for the single most likely future and optimizes hard for that. But if the prediction's right, then that's fine, but there's a good amount of instances where that's going to be wrong and you can't do anything about it by that point. So our method holds a distribution of threat scenarios and optimizes expected values across all of those. And then it allows us to have a model that can adapt to whatever move the adversary makes after. So this is kind of how our pipeline works. So we have 5 stages here. So first there's the current assets, which each has like a carrying location, a readiness score, quantity and status. And then from there, we generated sets of threat scenarios from uniform with no signal all the way up until like skewed toward a high signal. And then this allowed us to fully cover different adversarial mixes that you might run into. And third is the composite expected value, which will be abbreviated from here on as CEV, which scores all the placements and weighted scenarios at once instead of betting on just one. And then fourth, we have a Bayesian adversary that observes the placements and then adapts its attack. And then finally, we have robust CEV, which is a way to optimize against that adapted adversary, and it will just repeat until placements stop moving. So everything's driven by the main objective, which is to make the posture the most efficient. So that looks like getting your readiness up, increasing your geographic coverage while lowering sustainment costs. So for our experiment, our simulation environment consisted of 20 military assets across 5 Indo-Pacific bases, which included Kadena, Anderson, Iwakani, Camp Smith, and Diego Garcia. And we had the strategic value set between 0.78 and 0.95 over 10 decision steps. And we compared the three main methods head to head. So greedy baseline, CEV optimizer, and robust CEV. And from there, we were tracking the readiness, the geographic coverage, and sustainment costs to get our overall posture efficiency score. So every result here is averaged over 10 random seeds. So this specifically is greedy versus random. And on posture efficiency, greedy loses to random placement by about 25%. And the reason for this is because 20 assets fits 4 of the 5 equal capacity bases. So greedy will always leave the 5th one, which in this case was Diego Garcia, open. However, random will spread across all of the different bases, so that allows for a higher and less predictable placement. So then with experiment 2, CEV is able to recover 20% almost efficiency over greedy. And the advantage widens as uncertainty grows. So that's, sorry. This 31% of dynamic programming buys over greedy dispatch is similar to that in like published medevac literature. So this is like a decently meaningful gain that it would actually be useful in one of these scenarios where you have high uncertainty or a lot of moving variables. And for experiment 3, this is where we introduce an adaptive adversary. So it observes where we place and then updates its attack, and it's re-optimized against the attack. So robust CEV is used to iterate until the loop reaches a stable equilibrium, and then our new placements can't be exploited. So robust CEV catches the shift in its first iteration. It can redistribute to a location that the attack doesn't touch and hold up. And then it'll continue to do that. And in one of our experiments, it was able to get a 158% improvement over the native optimizer, which was a greedy heuristic. So robustness isn't always necessary, but it's very decisive when your prior has a poor guide to real intent, because if you're being deceived in any way, it might become difficult for your model to detect that. And so for experiment 4, this was basically more focused on speed. So across every size we tested, from 10 by 5 up to 200 by 30, all 3 can finish this solving within under a millisecond. And the reference operational planning ideal window is 4 hours. So the ability to run all of these tests like in a high pressure situation where you don't have a lot of time on hand is really easy, and it's really efficient. And then as for experiment 4B, we swept a Wasserstein ambiguity radius to control how much doubt we're planning against. And below 0.2, nothing really changed. But as the radius increases, there's a sharp increase in cost. So yeah, past that threshold, it'll climb to over 18.3% and at a 10.7% premium in a nominal placement quality. So the signature is a pretty like well posted trade-off here. And targeting epsilon around 0.4% has only a 2.1% quality cost. So as for experiment 5A, we ran the comparison across different European theaters, bases, and different threat mixes. So the ordering of how the models performed held over every base despite the difference in like geographic information and placement information. And the reason for the smaller European gap compared to Indo-Pacific is mainly due to a tighter geometry because 6 closely spaced bases led to like fewer options for placement. And then as for experiment 5B, which I believe was our last experiment, we tracked our expected values, and they track within 0.2 of the actual value in both cases on worst case readiness. So readiness numbers weren't the difference between the two theaters. This is how we were able to find that it was mostly a geographic thing. So traditional planning, essentially what we found, is pretty predictable and that can be exploited. So these CEV fixes can plan across many futures at no extra computational cost or losing time. Robust CEV can extend to fix the adapted adversary and account for any changes in the plan without fully committing to a bad placement. So the main conclusion we came to after doing all these experiments is that you shouldn't just optimize for one future, but you should optimize across many possible futures and think of what all the different worst case scenarios are and make your decisions based on that. And that robust planning has a lot of higher, stronger posture. So the advantage is really large when the situation's most uncertain. But yeah, so as for like future work, using reinforcement learning instead of fixing it per rule and scaling for larger threats would probably be the next steps. And then from there, just integrating it into real world workflows. But yeah, I think that was it for mine.
Awesome. That's amazing, Amelie. I really enjoyed your presentation and really appreciate all the hard work you put into this over the summer. You should be really proud of the work. Yeah.
Thank you.
I do have some questions and I'll follow up after. And just want to say thanks once again and great job.
Okay, for sure. Thank you. Have a good night.
Yeah. Hey, Abuka.
Hi, good evening.
Good evening. Okay, are you ready to go?
Sorry, give me a second. I'm trying to look for, okay. I don't know if you can see my screen.
Yeah, can you try to make it full screen though?
Okay.
Okay, perfect. Yeah, feel free to go whenever you're ready.
Okay. Okay, hi everyone. I'm ready now. So, hi everyone. Good evening. My name is Ibuka Chidbem Uzoma, and I'm a research fellow with Anote AI. So, today I'm presenting my affiliation study on semantic chunking and hybrid retrieval for financial document Q&A, which is run on the finance bench. So a simple question, does adding complexity to like a retrieval pipeline actually help on financial documents? So basically I tested like a fixed chunking baseline against semantic chunking and a full hybrid pipeline. And I ran the whole comparison twice independently to make sure like the results actually held up. And oh, for the setup, the financial filings are long, they're table heavy, and cross reference exactly the kind of documents people point to when they want to justify adding more machinery to like a rack pipeline. So I just picked the five most common upgrades, which is the most common upgrades: semantic chunking, the metadata, query expansion, hybrid search, re-ranking, and asked a narrow question: do they actually beat a plain baseline? Okay, so going into like the three pipelines, um, the same generation model throughout, only like the retrieval side changes, and for the baselines, they you have like the fixed width chunks, the plain TF, IDF, and which is and the control. And for the semantic, we have one change, chunking on paragraph and sentence boundaries instead of like a fixed word count. And for hybrid, we have everything stacked, um, the structure aware chunking, metadata prefixes, the BM25, which is the TF IDF fusion, the HYDE query expansion, and the lexical re-ranking. So now we'll talk about like how it was run. So it just comes in five basic steps, which is first of all a stratified sample of 14 questions across 11 filings, and three pipelines built identically apart from like the retrieval. And every question scored on the rogue L F1 and the exact match. And then an independent rerun actually was taking place, and from the fresh PDFs, fresh retrieval, and a separately like written sets of answers. So there was no picking out at like one of the run that we actually did. And lastly, there was a bootstrap test to like get real confidence intervals instead of like eyeballing the differences. So going into the results, so for the headline result, the baseline won in both runs, and the semantic scored lower both times, down from 0.035 and 0.023. And the hybrid for hybrid, five techniques combined also score lower both times, which is for down from 0.024 and 0.021. And added, the complexity moved the score the wrong direction twice, not once. And now thinking about for this slide, we're wondering whether it is real or it is a noise. So I didn't want to like call a drop real just because like the average was lower. So I actually bootstrapped the confidence intervals on the differences. So the semantics dropped in like in round one, which is like statistically significant, and the whole interval stays below zero. And the other three drops are directionally consistent but don't clear that bar on their own. So one solid finding is that the three weaker signals pointing like in the same way. And going to like the weak spot, this is the slide most likely to like I have questions based on because I was really not convinced, or I wasn't satisfied. So like I did multiple testing, and so I what I actually eventually did here is that I broke down the question type, the every pipeline, the baseline, the semantic, the hybrid, and scored zero, and everything scored zero exact on like the exact match on the numeric questions. So not lower zero or every conditions, but for like both runs that I carried out. And there wasn't like a bug, and I was trying to like find a bug here, but like I wasn't able to find it. And none of the three setups ever like surfaced the correct number to the model at all. So that's like a retrieval failure, not like a reasoning failure. So after that, um, after the which is like the post hoc analysis, I diagnosed like the three concrete causes of why this issue was really prominent. So the needed number and its rows label were split across like separate chunks. And some answers required combining figures from two statements that never appear together, and some questions used shorthand like the capex or the DNA that never appears verbatim like in the filing. So I fixed all three and reran the five numeric questions that had failed. And four came back exact, while the fifth one was correct in substance, but like sensitive to like rounding. And this diagnostic, not a fourth condition, and this is like a diagnosis, which is not like a fourth condition that I built, it knowing like which questions had actually failed. Okay, so coming like into like the held out check, so I tested it on questions it wasn't built around. So 10 fresh questions from 10 companies never used anywhere in the main application, and which scored blind with no tuning at all. So the baseline got 6 of the 10 exactly right, and the fix got 5 of the 10. So it didn't beat the baseline. What it did do reliably is like solve like the exact problem it targets. Like for instance, PepsiCo's EBITDA margin needed two statements combined, and the fix caught both. But it also introduced like two new misses, which is the Coca-Cola and the Amcor, where the baseline simpler chunking already worked, which is like a real fix, but it doesn't generalize into a blanket win. And going into the findings, the semantic chunking reliably underperforms the baselines, which is significant in run one. And then the full hybrid stack doesn't recover that loss, even like combining five separate enhancements. And the exact match failure wasn't sorry, the exact failure was fixable in the cases that I diagnosed, but the held out test shows the fix ties the baseline rather than beating it. And for the limitations, so uh, I guess some of the limitations include like small sample, which was just 14 questions with only four numeric ones, and one model, one retriever stack, and a conservative floor, not a ceiling. So two runs is also, I guess that was also like a limitation too, and not a multi-seed. It wasn't like a multi-seed study, and um, one filing dropped, and which failed to parse under like two extractors, and the evaluation wasn't blinded except the held out except on like if you go back to like the held out slide, which um yeah, that I was mentioning about the um yeah, so except on the held out side, which I was mentioning about like it didn't beat the baseline. What it did was reliably like just solve the exact problem it targets. So, and then which also like state like the run actually scored blind. So I would say for because I was looking at going into like the related work. So I was looking at the research papers that are actually related to this study, and seven of these papers actually underneath this. So the finance bench is the benchmark itself, and I know SETI LL is like the closest prior work, and actually found gains where I didn't find at all, which was worth flagging as disagreement. But the rest of them confirm numeric table reasoning is hard, and tables need like retrieving as like intact units. And for the BM25 kind of like beat a new neural retrieval on this document type. And also metadata helps alone, but it isn't like guaranteed combined. And the finance tuned embedding do not like they do actually outperform the general ones. So in summary, the bottom line is that uh, three takeaways is the the plain baseline is legitimate, which with fixed chunking plus the TF IDF is which is a real default, but not a straw man to like automatically upgrade past. And complexity doesn't compound for free, which is combining like five enhancement, adding added risk without payoff. And also a diagnosed fix still needs a held out test. Mine solved every failure it was built for and still only tied the baseline once I actually tested it on fresh questions. And for needs for next steps, four things in order. I think the next thing I'll do is swap the TF IDF and the BM25 for neural embeddings, which is my top priority. And everything here, including like the fixes lexical, like it can breach a query term absent from the source text. And secondly, I'm going to retest the fix at a larger held out scale with 10 questions, and one draw is a start, not like a verdict. So, and then lastly, I'm going to make the statement diversified. I'm going to make the statement diversified within a retrieval condition, wait, in a retrieval condition, which is only like trigger it when the question itself needs it to avoid the regressions without losing the case it solves. And also, um, once tightened, I'm going to promote the fix to a real fourth condition and run with the same to rerun, which is bootstrap treated, the bootstrap tested treatment as the other three treatment. And that is it for this presentation. Happy to take any questions.
Hey, Buka. Thanks so much for an incredible presentation. I really enjoyed it, and you did an amazing job this summer. So thanks so much, and you should be really proud. I'll send you some questions offline.
I'm sorry?
I just want to say thanks so much for an amazing job, and I'll send you some questions offline, and really appreciate your hard work. So
Okay, thank you.
thank you. Awesome. Thank you, Ebuka. Really good job. Hey, Aitong, how are you doing?
Hi, I'm good. How are you?
Doing really well. Yeah, doing well.
Yeah, I'm ready to present my research. Oh, can I start right now or?
Yeah, you can start sharing your screen and then you can get started. Yeah.
Okay, no problem. Uh, um, let me see.
Can you hit like the slideshow button and let's see if it works?
Oh, not this one. Wait. Mm,
Okay, that's perfect. Yeah.
Okay. Yeah, hello everyone. Today I'm going to present the Annotate bench, which is a benchmark built around a practical question when label data is limited, and how should we spend annotation budgets? In particular, which example should we label, and how many labels do we actually need, and when does further labeling stop being worthwhile? Before training a classifier, a team with a fixed budget already face three decisions. The first is the example selection. Which items from the unlabeled pool should receive labels? And the second is the stopping point. Should we click 100 labels, 500, or 1000? And the third is the annotation source. Should the labels come from humans and LLM or a combination of both? These choices affect cost as well as model quality, but a single final accuracy score cannot tell us whether we selected the right examples or pay for more labels than we needed. That's the decision problem that Annotate Bench is designed to study. Our central research question is under a fixed annotation budget, which strategies produce the strongest downstream model? We answer it using three connected views. First, learning curves show how quickly each strategy improves as the budget grows. Downstream micro F1 tell us whether the resulting labels are useful for training a classifier, and cost performance frontiers show which combinations provide the best value. My contribution is not a new active learning algorithm. Instead, I built a reproducible benchmark pipeline that compares four selection strategy across 10 datasets and five annotation budgets. Under one control evaluation protocol, it produces learning curves, cost performance, frontiers, and an LLM labeling extension. This allows us to compare annotation choice fairly and connect them to a practical budget decisions. To make that comparison more meaningful, we need to keep the rest of the pipeline control. These slides show that control design. Across 10 public text classification datasets, we compare four selection strategy and five labeling budgets. In each condition, a strategy selects example from an unlabeled pool. We review the goal labels, train the same TF-IDF and logistic regression classifier, and evaluate macro F1 together with estimate costs. We repeated this across multiple seeds and cost scenarios, producing 3,000 measure result rows. The ultimate extension changes only one step. Instead of revealing goal labels, GPT-4o Mini generates the labels. The downstream classifier remains the same. They let us connect performance differences to the annotation strategy, budget, or label source, not a different training pipeline. So, under this controlled comparison, does one selection strategy consistently win? The answer is no. Um, no strategy wins universally. Hyperactive learning ranks first on 5 of the 10 datasets, so it has the largest number of wins. But random sampling and uncertain sampling each win on 2 datasets, while the diversity sampling wins on only one. However, the winner changes with the dataset and budgets. In several cases, the top confidence interval also overlap, so a small ranking difference may not be reliable. Random sampling therefore remains an important baseline. Greater complexity does not guarantee more useful training data. The identity of the winner is only one part of the decision. We also need to know how much data is enough. So, financial phrase bank illustrate the second question. At small budgets, the strategy behave quite differently. As the numbers of labor grows, uncertainty sampling improves substantially. At 500 labels, it reaches a macro F1 of 0.755. What matters here is the shape of the curve after the point. Moving from 500 to 1000 labels creates almost no additional improvement for the leading strategy in this setup. If we reported only the results at 1000 labels, we should miss the useful decision. Nearly the same performance was already available at half that labeling budget. So learning curves do more than rank strategy. They reveal where the value of additional annotation begins to flatten. The next step is to express that decision in the unit organization usually care about, which is the cost. Here, each point represents a strategy and budget combination. The vertical axis shows the macro F1 and the horizontal axis shows the estimate direct cost. The black line here is the parallel frontier, the options for which nothing else is both cheaper and better. This separates two decisions that are often mixed together. The highest point gives the best performance, and the frontier show which choice are efficient at different spending levels. The outend points appears further left because the direct API cost is lower, but this excludes human review, retries, latency, and quality control. So, cost therefore help us compare annotation choices, but cost alone does not tell us whether the generated labels are useful. This brings us to the LM extension. In these figures, the horizontal axis show the agreement with Go labels, and the vertical axis show the downstream F1 gap from the best Go label strategy at the same budget. If accuracy determines downstream utility, high agreement datasets would all sit near the zero line, but they do not. For the yield polarity, the agreement is 0.972, and the downstream model almost matches the best Go label results. The financial phrase bank also has a high agreement at 0.929, but its downstream model still trails by 0.045 micro F1. And the AG news shows an even larger downstream gap. So we must ask not only how many labels are correct, but where the error occurs and what models learn from them. An LM annotator should therefore be evaluated as a complete annotation strategy, not only through label agreements. So far, the benchmark has used TF-IDF with logistic regression to keep the comparison control. We then repeat the evaluation with sentence transformer embeddings. Performance improved on 8 of the 10 datasets, with particularly large gains on 20 newsgroup, emotion, and tweet eval sentiments. However, the change is not uniformly positive. As we can see, the yield polarity changed very little and the track performs worse. These robustness checks show that annotation strategy and downstream representation cannot be treated as completely separate decision. An example selection method is useful only in relation to the model that will learn from the selected data. Taken together, the results suggest three practical recommendations. First, do not choose an annotation strategy by default. Compare learning curves on the target datasets and the budget that actually matters. And the second, stop at an efficient point when further improvement no longer justifies additional costs. And the third one is evaluate LLM labels downstream together with their error patterns and the real cause of quality control. The benchmark also have some limits. It focus on text classification and simulates annotation by revealing Go labels, so it does not capture human disagreement, fatigue, and ambiguous instruction or interface effects. They're not just caveats, they define the next stage of the research, measure human workflows, supported task types, and more complete evaluation of LLM assisted annotation. So to conclude, Annotate's bench treats annotation as a decision that should be tested empirically. There is no universally best selection strategy, and learning curves helps identify when to stop, and how label accuracy does not necessarily produce an equally strong downstream model. So the main message of this research is do not benchmark annotation in the abstract, benchmark the decision you actually need to make. Thank you. I'm happy to take any question.
Hey, Aitan, thanks so much
Hi.
for a really amazing presentation. Just want to say you should be really proud of this research. Really enjoyed your talk, and
Yeah.
yeah, I'll follow up with a few questions like afterwards, and just wanted to say you should be really proud, and thanks for doing a great job. Yeah.
Yeah, thank you.
Okay. Take care, Aitan. Yeah.
Bye. Thank you.
Hey, Susanna.
Hey,
How are ya?
good, good. How are you after almost 4 hours? Oh my gosh.
Doing good. I've been learning a lot, so it's been a very
good.
great day. Yeah, you can test your screen share if you want. Just make sure you're all good to get started. Yeah.
Yeah, let me open it up real quick and make sure. Okay. Yes, are you able to see my screen?
Yeah, you should be good to go.
Okay, awesome. Alrighty. So I'm Susanna, and today I'll be discussing the paper I was working on, dev intent, and answering the question of how much does LLM generated code violate developer intent? So to get us started, I want to answer what exactly an intent violation is. So for the definition of our purposes, we just chose to define it as whenever an LLM is given an ambiguous prompt, it could generate code that fails to properly capture design, like implicit design or instructions that the developer may have wanted included. For example, take the ambiguous prompt, return only the unique items, and then compare it to the clarified prompt where it specifies to return the unique items sorted in ascending order. But why does it even matter to actually make specifications like that? So to get more into detail about why it matters, we can break down the example a little bit more. From the ambiguous prompts, here's two ways it could be interpreted. Of course, these don't capture all cases, but for simplicity, let's just assume these are the only valid ones. The first one asks for items to be sorted in ascending order, producing this output on the left. And the second one specifies to leave the order as is, producing a different output that you can see on the right. The initial prompt is the same, the core task is the same, and yet depending on how an LLM chose to fill in such gaps and holes, we're going to get different outputs. So to measure these intent violations, we chose to introduce the metric of the intent violation rate. And this essentially just asks us, of the solutions that satisfy the given problem's visible tests, what fraction of solutions violate the developer's actual intent? Or in simpler terms, it's just the rate at which an LLM's code produces a solution that passes visible tests and fails at least one hidden test. Before we move on, though, let's actually break down a little bit more about what goes on into the IVR and what it's calculated on for some context. So looking back on the example, the ambiguous prompt is, as said before, return only the unique items. And in the benchmark, we define the clarified prompt as return only the unique items sorted in ascending order. So these are the two types of prompts that we have in our benchmark, the ambiguous and the clarified. In addition to the two types of prompts we also have two types of tests, stated tests and hidden constraint tests. Stated tests are what is visible to the LLM. So if we refer back to the example, the test would only verify that the solution produces an output that returns only unique items. It just tests the core task at hand. Hidden constraint tests are, as named, hidden from the LLM. These tests capture any behavior that is implied in the ambiguous prompt, but defined in the clarified prompt. Now, for this example, we only defined one hidden test. However, for other problem specs in our benchmark, there was a wide range of about 1 to 3 constraint tests per problem that we had. In our experiment, we structured each problem in the benchmark as such, where we provided the LLM with the ambiguous prompt and C1 the stated test. The rest of the structure remained completely hidden, with the clarified prompt for our use and the hidden constraints serving as tests to determine whether the LLM produced code that passed implicit intent. The hidden constraint tests were formed by stripping the clarified prompt into deterministic test cases before we reached the ambiguous prompt. So based on the information we provided in LLM, for each ambiguous prompt and stated test, it would produce 5 solutions. And for each problem, all solutions produced were tested against the stated test and the hidden constraint test that we stripped from the clarified prompt. Then the IVR is calculated focusing only on solutions that pass the stated test. This meant that if it didn't pass the stated test, it was not included in the calculation for the per problem IVR. In this case, with 2 out of 5 solutions failing, it would produce an IVR that only accounted for the 3 passing solutions. The reason why we chose to do this is because if a solution doesn't even meet the baseline criteria to pass the core task at hand, then it doesn't meet functional correctness standards. Therefore, the solution's basically ineligible and doesn't even answer the question at hand. So once we narrow down on the 3 passing solutions, we can see that if all 3 of them pass all hidden constraint tests, then it would produce an IVR of 0. However, if all 3 fail all of the hidden constraint tests, then we would get an IVR of 1. Another option would be if only some of the solutions pass hidden tests, then it's simply that pass ratio. In this case, if 2 pass, then only 1/3 of the eligible solutions violate intent, which would give us an IVR of 1/3 or 0.33. So what did we actually find after running the experiment on 49 different problem specs? So we tested on Claude Sonnet 4.6 model and OpenAI's GPT 4.1 model, and we found that both passed over 92% of the stated tests. So there were still some solutions generated that didn't pass the initial baseline. And of the passing solutions each model produced, that we found that over half had failed hidden constraint tests. Therefore, over half had violated intent in some way. Note that the confidence intervals for both models overlapped, so the gap of about 10% between the two isn't actually statistically significant here. And for a deeper look at the IVR, here are some breakdowns for the constraint test fail rates. What stands out the most is the contrast between the stated tests and the hidden ones. The stated tests on the previous slide showed that the models for both of them failed only around 6 to 7% of the time, but every hidden constraint test fails far more often. So the visible test being passed tells us very little about whether the model captured the intent underneath it or not. And when we decide to look further at the distribution of the IVR in both models, we can observe that solutions tended to cluster at the extremes of IVR 0 or IVR 1. And this behavior actually suggests that the intent violations are somewhat systematic and not purely sampling noise. However, if they were due to sampling noise or random variation, the per problem IVR would have been spread out more evenly across the intermediate values, but we don't actually see that. We instead see that both dependent models produced outputs to or fully captured implicit intent. Finally, in the future, we hope to expand on the benchmark. Currently, it only sits at 49 problems, but it's ideal to increase that number to at least 100, which is a similar size to other benchmarks in very similar research. Additionally, with this, the goal is to build towards improving under-specification detection, as the root of this paper stems from developers providing LLMs under-specified or ambiguous prompts, which would often lead to gaps in code and solutions that it would produce. Also, we only tested on 2 frontier AI models, Claude Sonnet 4.6 and OpenAI's GPT 4.1. In the future, we hope to see how it works with other models such as Qwen or Kimi or Gemini and other various types, and also across other types of problems like data manipulation or even on refactoring existing code. Thank you. Happy to take any questions now.
Thanks so much, Susanna. You did an amazing job this summer, and you should be really proud. I guess I was wondering if you might have a few seconds. I think it'd be cool if you also showed like that product video you were kind of filmed with like the UI, just to kind of talk about some of the product work you did too, you know?
Oh, absolutely. I'm more than happy to. I can actually, do you want me to show the video or just the website that's been deployed as is? Because I'm pretty sure it's up and working.
Yeah, you can show the website as is if you have some time, yeah.
Okay, yeah, of course. Let me open up the website. Hold up really quick. Alrighty. Okay. Let me know if you cannot see my screen, or if you can.
I can see it. I'll let you take it away.
Okay. Awesome. Okay, so this is on my test account, so that's why everything you see is like testing or testing. But to showcase a little bit more, I was working on the web app. So this is very similar to like ChatGPT or Claude's chat option, or just like Gemini when you Google something. So pretty similar layout. And right now we're able to do messages like, let's say, hi. And let's see. And so we'll get a response. Currently, what's working is that it's working through an API, whether it's through OpenAI's API, Claude's, Gemini's, whichever one is provided. With this account, it should be with OpenAI's. And that's where we're getting our responses. It supports, if it will open, file and document uploads and things of that nature. So let me upload some Anote relevant documents. So once these files are uploaded fully, we've also chose to include the ability to view the file inside. So here I just uploaded a draft of my initial research paper, and you're able to go through it and see more clearly how it works. This is another draft that I had for it. So that's a nice option. Currently, we also have the library feature where you can see like past files that I was testing with from like a class I had. And we provided file organization. So if you go into cheat sheets or lab testing, you can see there's files past there that have already been organized. You are able to view the files. However, these files I just uploaded, so not now, but these ones I did. So we're able to view them in here as well. And you're able to organize them just for your own use. However, of course, within each chat, the files that you upload in that you view in library are only accessed within the specific chat they were uploaded in, so context doesn't travel between chats currently. The search chats function, so test, communication, so that's there. And then if we go back, we're able to also have users regenerate responses if they want to. Obviously, in this one, it's choosing to not give a different response, but in perhaps a different option. Yeah. And then another big thing that I was working on was just the UI for the settings. So users can now upload their photo, they can modify their name. So if I change that to be that, we'll have my name there, my photo. If I choose to upload it, it'll be uploaded. Right now, the account settings, it's pretty bare bones, nothing too much yet, but I'll be working on a little bit more to flesh it out a little bit more. Currently, as you can see, I'm using the model for GPT 4.0 Mini. However, we do provide options for users to set their own through Claude's, GPTs, or Gemini's, and then they can also select their own versions. For usage, we have tracking pretty easy, so it's easy to see how users are tracking, and then users are also able to purchase more credits through here through through a Stripe configuration, and the same is true for the billing and subscription. And then the display is just if you want it in dark mode or light mode. And then that's about it for the product right now.
Awesome. Thanks so much, Susanna. I really appreciate
Of course.
You taking the time to present today. And thanks so much for not only your work on the research, but also the product. And
yeah, happy. Yes.
Okay.
Awesome. Thank
Well,
you.
have a great rest of the night. Yeah.
Thank you so much. Have a good rest of your night.
Yeah. Oh, hey, Hannah. So I think after Sharon, you'll be up. Let me just message Sharon really quickly, and then you should be good. Hey, Sharon, how are you doing? Awesome. Yeah, feel free to get started whenever you're ready. You can share screen and take it away.
Wait, so do I have to give an intro or anything, or do I just go? Like, do I just introduce myself, or do I just go?
Yeah, I'll just go full screen really quickly.
Okay. Oh, wait, no.
Yeah, I think you can just kind of go and take it away. You could give an intro if you want.
Oh, okay. So, hello everyone. My name is Sharon Zhang, and I'll be presenting my paper that I worked on during my time at the Anote Research Fellowship. My paper is titled "Beyond Pass at K: Measuring Reliability and Security of Agentic Code Generation." And so my paper will look at two independent failures in agent evaluation. The first one being the misapplication of the metric pass at K. This mathematical misapplication was discovered through a violation of one of the assumptions of the metric, and then we looked into replacing it with a new metric that we'll get into in this presentation. The second failure was a security blind spot, and this would be covered in a separate presentation by my research partner. So to understand our research topic, I'll be discussing some background topics, first one being LLM code generation and sampling. So the term token by token generation looks at a probability distribution over the next tokens in an output and how it predicts the following tokens by taking a sample from the current token. And a variable that can control the output, the prediction of the next token is temperature. And for example, by decreasing temperature, we will get more deterministic and predictable outputs. And increasing temperature, we would get unpredictable and more varied outputs. So this is important to understand, as the same prompt given to an LLM would create different outputs, and repeated runs will yield different completions. This is an expected behavior and not a bug, as it reflects the real uncertainties in the model's prediction in the real world. So how does this connect to my research of PassAtK? Well, PassAtK leverages this variance in outputs by sampling K completions and checking if any pass, estimating the probability that at least one correct solution emerges from K tries of an agent. And speaking of PassAtK, we'll discuss a little bit of the metric itself. The metric is presented on the left-hand side. It estimates the probability that at least one of K randomly chosen samples from the N generated is correct. And this only works under two assumptions. One being each of the N samples in an independent draw from the model's output distribution, and two, N is reasonably large relative to K in order to stabilize the estimate. And we'll see in our experiment that the first assumption will be violated in agent evaluation. So the final topic we'll discuss is the difference between completion-based code generation and agentic code generation. So completion-based code generation is what PassAtK relies on, as it is a simple, stateless one-shot call of the agent that is being tested. This is a cheap and fast enough way to sample the agent many times, and this causes it to not be as produce as reliable results compared to agentic code generation. This is a multi-step loop, including planning multiple tool calls, observing the tool, and going through multiple iterations. This obviously is more expensive, a little slower, and has different varied side effects. This means that each run must be a deliberate attempt and compared to a cheap sample. This connects to the reality of what engineers do when they want to pick a reliable agent, as engineers want to run an agent once and have it give an accurate output. They can't afford to be running an agent 50 times and picking the best out and cherry picking the best output. This is where we implemented reliability at K as the new metric, as it reflects this reality. It measures the odds a single deliberate attempt works and estimates from just a modest number of repeated runs of an agent. So finally, going into the research itself, we looked at 3 research questions for the first part. First one being, does substituting unit test counts for rollout counts break the PassAtK estimator? So this looks at the violation of the first assumption, where we really see the importance of independent draws of an agent when testing reliability. The second research question is, how much does a broken metric PassAtK inflate the corrected reliability at K? So we'll see how big an error does PassAtK produce when looking at reliability of the agent. And then finally, the third question we look at is, can a cheap single rollout proxy substitute for repeated multi-rollout runs? So does the more expensive multiple runs of an agent is it better for testing reliability in the long run compared to just running an agent once and seeing the results and then just hoping that result is accurate? So we go into the experimental setup. We tested 3 synthetic agent profiles, including Agent X, Claude Code, and Codex. And we gave each agent 10 curated tasks, ranging from 3 easy 3 mediums and 4 hard tasks. There were 8 independent rollouts for each pair of task and agent, which resulted in 240 total execution results. And from those execution results, we concluded the following. So for the first research question, we found that the pass at K metric was broken as it calculated reliability purely from test suite size. So for example, we see that agent A had 4 out of the 10 test cases pass, resulting in a score of 0.4. And then agent B had 2 out of 5 test case pass, which also resulted in a score of 0.4. And from pass at K, the scores are given. Agent A was 0.976, and then agent B was score of 1. And we see that agent B scored 0.024 higher from just the test count alone. This showed that these tests were not independent of each other, which violated that first assumption of pass at K. And then this goes into the part where we implemented reliability at K, and then we see the errors, how big the error inflation was between pass at K and reliability at K. So what was interesting about this part of the experiment was the ranking of the 3 agents we tested remained the same. We see in the gray columns that show pass at K, agent X had the highest score, 0.97, with the following scores for Claude Code and Codex being 0.96. This showed nearly perfect reliability of these 3 agents, but then the corrected reliability at K metric showed the same ranking, with agent X being the highest at 0.13, and then Claude Code and Codex being at 0. But these lower scores were obviously much lower, showing low reliability. So therefore, the rankings held, interestingly enough, but the scores meaning was transformed. And then to further support the difference between reliability at K and pass at K, there was a mean absolute inflation of 0.924, which was far above the 0.5 hypothesized threshold. Therefore, pass at K can not be trusted with evaluating agents. And then finally, we look at the result for our third research question. We found that cheap single rollout proxies fall short, and we should be considering to use multi-rollout data. So going into this, we tested the proxy value score for each of the 3 agents, as shown on the graph on the right. And even though all the agents had varying proxy scores with the different colored dots, they spread across all, like the horizontal x-axis, but their reliability at K score still remained at around the same level, being 0. This shows that the single rollout proxy score can't be the best way to track true reliability. And to further support that, we found the Spearman correlation to be 0.465 across all 30 task agent pairs, which was well below the 0.7 threshold, again supporting that the agents should be tested multiple times in order to get a better accurate representation of their reliability. They can't be tested just once and then use that one test to predict their reliability in the future. So to summarize, we found in the first part of the experiment that reliability doesn't come for free. We found that pass at K, the assumption with independent draws was broken. And in our second research question, we found there was an incredible difference between using pass at K and reliability at K. And this inflation caused an inaccurate representation of our agent's reliability.
And then for our third research question, we found that cheap proxies fall short of showing the true reliability of an agent. So only reliability at K estimated from repeated independent rollouts will tell you the odds of a single deliberate attempt succeeding. And that's the end of my presentation. Thanks for listening.
Yay.
Okay,
Thanks so much, Aaron.
Okay,
Really appreciate you doing an amazing job this summer, and you should be really proud of all your hard work. So,
thank you. All set?
yeah, I'll have a few questions. I'll ping you on the side, but thanks so much. I really appreciate your time.
Okay, thank you so much. Bye.
Hey, Hannah, how are you?
Hey.
Yeah. All right. Yeah. Take two. Let's go.
Turn two. Cool.
Yeah, feel free to share your screen and get started whenever. Yeah.
Sure. Okay, let me just check if it's sharing. Okay, cool. So I'll just get started. Hi guys, I'm Hannah, and together with my teammate Ziray, we were working on the paper retrieval bench this summer. So today I'm gonna do this presentation will be about this retrieval bench, chunking and embedding choice as a first class variables in cross-domain retrieval evaluation. So let me start with the motivation. When people build a retrieval system, say for a RAG pipeline, they face two early, seemingly independent decisions. The first one is how to chunk their documents, and second one is which embedding model to use. The conventional wisdom treats this as minor engineering choices. You pick a popular embedder, you pick a default chunk size, and then you move on. But we challenge that assumption. Our central claim is that chunking strategy and embedding choice are first class variables, meaning they have effects on retrieval quality that are large, interacting, and domain dependent, and therefore deserve the same rigorous control study we give to the model architecture or training data. The problem with existing retrieval benchmarks like BEIR is that they evaluate on a fixed corpus of atomic passages. They freeze the chunking decisions, so they cannot tell you anything about how much chunking matters related to embedding choice. And we designed the retrieval bench specifically to answer that question. So how is the benchmark structured? The key idea is to take the same source documents and index them under different segmentation policies, then retrieve with different embedding models. This isolates the two variables. The design crosses four independent axes, the 12 domain, different text type draw from established IR datasets, and we have four chunking strategies, fixed window, sentence, recursive, and semantic. And we use the three dense embedding models. One is OpenAI text embedding 3 small, one is BGE small, and the other one is E5 small. As for the BM25, it includes as a sparse design for the benchmark. And the full experiment complete cross product, every domain and every chunker and every retriever. And that's what let us decompose how much of the quality variation comes from chunking versus from embedding. And we will come back to the decomposition in the metrics section. The core research question is, how much does the chunking strategy matter related to embedding model choice? And does that ratio change depending on the domain? And now let me walk you through how the data is built, because the construction has a few details that matter for interpreting the results. Each of the 12 domains reuses existing IR datasets, so queries and relevance judgment are already exist. These include familiar BIR style sets like TREC COVID, 5QA, Arguana, NF Corpus, SciFacts, SciDocs, Natural Questions, Fever, HotPotQA, DBpedia Entity, Quora, and the Open Domain QA set. So there is an important caveat we state specifically. Because of this subsampling, the scores support comparison among configurations on the same sample corpus. They are not directly comparable to the numbers on full corpus leaderboards like BEIR. So when you see NDCG numbers later, the right question is chunker A versus chunker B on the same sample set, but not how does this rank against the BIR data boards. And this is a deliberate internal comparative benchmark. The 4 chunky strategies are the heart of the setup. So let me describe each one concretely. The first one is Fix 512. This is the most naive baseline. It cuts the document into windows of up to 512 white space delimited words with 50 words overlap between consecutive windows. Overlap is there to avoid splitting a meaningful span right at the boundary. The second one is sentence. This uses an NLTK to segment the document into sentences, then groups them into a non-overlapping windows of the 3 sentences each. So chunk boundaries always align with the sentence boundaries, more linguistically meaningful than splitting the mid-sentence. And the third one is recursive. This is a hybrid 2-level approach. It first splits a blank line paragraph boundaries. Then, for any paragraph that is still too long, it falls back to the sentence level splitting. And the idea is to respect the document's structure when it's available and degrade gracefully when it isn't. And the final one also is the most sophisticated one, is semantic. It greedily merges adjacent sentence as long as their cosine similarity stays at least 0.75. The intuition is sentences that are semantically close probably belong to together in one chunk. So the chunk boundary is placed where the meaning shift. Okay, note that boundary detection here uses OpenAI embedding model, and we flag this as a potential confound since the same model later also used as one of the downstream embedders. We will revisit it in limitations. And the key takeaway from this section is these 4 strategies span a spectrum from purely structured, like Fix 112, to purely semantic, like semantic chunking, with sentence and recursive sitting in between. The benchmark is essentially asking, across this spectrum, where does it matter the most? So finally, how do we score retrieval? The primary metric is NDCG at 10. There's a subtle but important detail in the system retrieves the top 50 chunks, but relevance judgment are at the document level, not the chunk level. So we max pool the chunk score up to their parent's document, meaning each document score is the maximum score among all its chunks, and then evaluate the top 10 unique documents. This means that chunking can't artificially inflate a document by producing many high-scoring fragments. One document gets 1 score. And all dense embeddings are L2 normalized and scored by inner product, which is equivalent to cosine similarity for normalized vectors. BGE and E5 also use their model-specific query and passage prefixes, which is the correct, fair way to use them. So now the most novel part of the methodology. To quantify whether chunking or embedding matters more, we introduce 2 indices via variance decomposition. The first one is CSI, the chunking sensitive index, roughly how much the score varies when you change only the chunker while holding the embedder fixed, average over all embedders and normalized by total variance. And the second one is ESI, the embedding sensitive index, the mirror image, how much the score varies when you change only the embedder holding the chunker fix, average over all chunkers.
So intuitively, if CSI is bigger than the ESI, changing your chunking strategy moves quality more than changing your embedded model, and vice versa. We also use a bootstrap confidence interval and paired tests. So comparisons comes with uncertainty estimates, not just the point numbers. And that's the full setup, the data, the four chunkers, and the measurement framework. The natural question now is what actually happens when you run this? And that's where I'll hand it over to Zure to walk you through the experiment and the results. And that will be all.
Awesome. Thanks so much, Hannah. I really appreciate you taking the time to do this. So, yeah.
Thank you.
All right. Well, I'll see you soon, and great job on this one. Yeah.
See you and have a good night.
Thank you.
Bye.
Hey, Aya.
Hello, how are you?
Sorry, can you say that again? I can't hear you.
Oh, I said hello, how are you?
I
I'm
can't. I
sorry.
can't hear you for some reason. Oh wait,
Hello?
try again. Oh yeah, that's better. Okay.
Awesome.
Cool. Yeah, feel free to share your screen and get started. Yeah.
Just give me 1 second. Just putting the presentation on. Should be this. What? All right. Can you see my screen?
Perfect. Yeah, feel free to start.
Awesome. Hello. My name is Aya Oyemami, and this summer I worked as a machine learning intern here at Anote. And over the course of the summer, I worked on three main deliverables, which were the Slackbot product, a research paper, and four go-to-market proposals for Anote. Today, I want to walk you through everything I built, what I found, and where each piece stands. As a machine learning intern at Anote, like I said, I worked on different deliverables, one of them being the Slackbot product, which is Anote's own Slack narrative AI agent. The second being a research paper under the topic of enterprise bench, which was testing whether tool calling accuracy actually predicts deployment safety. And the third deliverable was the go-to-market proposals for Anote. And all four proposals have been written and completed and submitted. The research paper is complete, and Anote's Slackbot has its core functions completely working, and we're moving into deployment. Let's start with the go-to-market proposals. All four proposals, like I said, have been completed, and each of them targeted a very similar pitch, which was showing that Anote isn't just another module vendor, but a trust layer that sits around any module, any labeling, any evaluation, and governance works that makes AI safe to actually deploy. The first proposal, one of the proposals I worked on was the AI CBIR Phase 1 proposal, which was responsive to the Army's AI and machine learning focused open topic. And it was built around a human in the loop data curation and evaluation pipeline for LLM and RAG systems. Another proposal I worked on was the Geospatial Research Laboratory CSO proposal, which was covering remote sensing and mapping, and GRL needed AI and machine learning classification across electro optical, FLIR, radar, and LIDAR sensor data for their terrain characterization. The other proposal I worked on was the SAM.gov proposal for the Air Force, and that was under shared infrastructure, standardized tooling, governance frameworks, and managed systems. And we mapped a proposal for every one of those capabilities and related it to every work Anote has done in the past as well. The other proposal I worked on was the DevCon ARL white paper, and that was, I believe, the most recent one, and that had to do with algorithm evaluation and constrained environment deployment. The next deliverable I worked on during this internship experience was my research paper, and that was enterprise branch, covering if synthetic tool calling benchmarks depict predict deployment trustworthiness. Enterprise Bench asked one question: do synthetic tool calling benchmarks predict deployment trustworthiness? And in plain terms, that means if an AI agent is good at calling the right tool or function, and does that actually mean it is safe to put in front of real users and real company policy? Yes, it might do exactly what you asked it to do, but does it follow every single policy that we just assume it does, right? And I measured this using five different dimension scores, which were the policy violation rate, the multi-turn consistency, composite score, force completion rate, and audit trail reconstructability. Being upfront about the status split, because being honest about what is measured versus what is still pending in itself is part of the paper's design. And on top of all this, I built a bootstrap confidence interval at the 95% level with 1,000 resamples into the evaluation pipeline. So every result came with real statistical grounding, not just a single number. I ran two agents against a system task policy annotated suit, and the first was a deterministic reference agent that was synthetically perfect by construction, meaning it always calls the right tool. and that agent still violated any applicable policy on 15% of tasks. The other agent that I ran was the live chat GPT for O Mini, and that was run on the same suit, which scored a comparable 56% violation rate. The 95% confidence interval for those two numbers overlaps substantially, which tells us the real effect, not noise. And it wasn't just random calculations, but both agents followed common scale. Um, and where they consistently broke down was on company specific rules, like things like internal IT permission limits that were never stated outright, but any real deployment would expect the agents to respect. The key takeaway was that success and deployment safety are different axes. Being right about the to call is not the same as being safe to deploy. And that's a core finding, and it is the same argument that runs underneath every one of the four federal proposals that I also wrote as well. The paper is complete, it's been posted to open review, and it's currently being posted to ArcSiv. Um, that's currently pending, but it's completely available to view on open review as well. The next deliverable I worked on during this internship, which was my favorite to work on actually, was the Slackbot product. Slackbot is Anote's own um, Slackbot is Anote's own Slack narrative AI agent, and it matters because it's not just like a mock-up; it's a working demonstration of some archetype we pitched in the past as well. Slack narrative had interface runs directly inside the Slack channels and DMs. So if you are creating a message and you have something that involves a document, it will prompt if you want to connect it to your Google Drives, or if you need like details from past messages, and it will reference that as well. It has a multi-step task execution, meaning it completes multi-step agentic workflows, not just a single turn question and answer. And the same, not just a single turn question and answer. And then it also sourced retrieval or RAG, and it looks up answers, like I said, from past information and cites its sources rather than just answering from like memory alone. And lastly, based off like Anote's core principles, it has that human in the loop approval. So it asks for human sign off before taking any consequential action. Um, and it makes sure the user is aware of everything on the background. Like I've said before, the full proposals have been completed and submitted. The enterprise bench paper has been completed and submitted to the necessary pages, and Slackbot also has its core functions complete as well, with deployment currently being done as well. So that's everything I worked on. Um, that's where everything stands. And it was an amazing experience getting to work with Anote and learning so much about artificial intelligence and writing these proposals and just being able to express all the work, all the amazing work that Anote has done. Hello?
Yeah. Just wanted to say thank you for doing an amazing job this summer. Really enjoyed working with you, and you should be really proud of all your contributions and accomplishments. So thank you.
Awesome. Thank you. It was also really great working and collaborating with all the other interns as well. as well as like Spreadsheet and Alyssa, and being able to like learn and push things forward. So it has been an amazing experience.
I'm really glad. Well, thanks for doing a great job with this, and really appreciate your hard work. So,
Yeah, thank
all
you.
right, take care.
Have a good one.
Bye.